The following is a conversation with Janna Levin, a theoretical physicist and cosmologist specializing in black holes, cosmology of extra dimensions, topology of the universe, and gravitational waves in spacetime. She has also written some incredible books, including How the Universe Got Its Spots on the topic of the shape and the size of the universe, A Madman Dreams of Turing Machines on the topic of genius, madness, and the limits of knowledge, Black Hole Blues, and other songs from outer space on the topic of LIGO and the detection of gravitational waves, and Black Hole Survival Guide, all about black holes. This was a fun and fascinating conversation. And now, a quick few second mention of each sponsor. Check them out in the description. It's the best way to support this podcast. We got Brain FM for focus, BetterHelp for mental health, NetSuite for your business, Shopify for selling stuff, and the AG1 for your health. Choose wisely, my friends. I do these longer ad reads up in the beginning. I try to make them interesting, but I do also make it super easy to skip with timestamps on screen and in the description. I do, however, try to make them personal, often related to stuff I'm reading or thinking about. Also, if you want to get in touch with me for whatever reason, go to lexfriedman.com/contact. And now, onto the full ad reads. Let's go. This episode is brought to you by Brain.fm, a platform that offers music specially made for focus. And when I say music, I mean audio experience. If you ever see me out in the wild, like a Starbucks, I'm usually either writing or programming deeply in focus with headphones. In those headphones are layers of audio, a mixture of some noise, beats, rain, layers, many layers that help me deeply, deeply, deeply focus. Speaking of audio, did you know that the Roman Empire used synchronized war drums to coordinate legions? Just imagine the sound of those drums. I need to do a lot more episodes on ancient Rome, on ancient Greece, on ancient China. Anyway, I'm not listening to war drums. I'm listening to Brain FM when I'm focusing. You too can increase your focus and try Brain.fm free for 30 days by going to brain.fm/Lex. That's brain.fm/Lex for 30 days free. This episode is also brought to you by BetterHelp, spelled H-E-L-P, help. It's raining outside, thunderstorms, like somebody's knocking on the window. If that's not a metaphor for prodding the subconscious mind, I don't know what is. Alan Turing comes up in this episode. He was crucial in the whole code-breaking effort in World War II. I should probably do an episode on that. His work, his person, his mind has been a presence in my life. What an incredible human being. But anyway, I think of the human mind, the conscious and the subconscious, is a kind of code. And therapy is a kind of code-breaking process. I wonder if AI will be able to help with that. Not just basic therapy, but ultra deep personalized therapy. Boy, that's a dangerous world. Anyway, check out a human therapist at betterhelp.com/Lex and save in your first month. That's betterhelp.com/Lex. This episode is also brought to you by NetSuite, an all-in-one cloud business management system. The more I study war, of course, the more I study business too, but war, the more I realize the importance of the organizational layer, of the supply chain, of the logistics, the stuff that nobody talks about, the stuff that most historians don't talk about. And actually, I've read a lot of James Holland recently and spoken with him, had the great honor of speaking with him, had the great joy of speaking with him and learning from him. And he's one of the historians that does look at the logistics, does look at the details of how everything is run. And NetSuite in the company setting is doing exactly that, the details of how everything is run. Because a business is not just a CEO with a bunch of sexy ideas or the late night engineer crouching over a table trying to fix a bug trying to find a breakthrough idea. Nope. It's also all the other stuff that actually make the thing work, make the thing efficient, have great tools to do so. Download the CFO's Guide to AI and Machine Learning at netsuite.com/Lex. That's netsuite.com/Lex. This episode is also brought to you by Shopify, a platform designed for anyone to sell anywhere with a great-looking online store. Since I mentioned history, the merchant networks were crucially important in ancient Greece, were crucially important in the Roman Empire, and of course, Genghis Khan. Very, very, very important. Of course, Genghis Khan was well known for protecting the merchants. And I think any empires, any civilizations, any state of the global affairs that protects the merchants from the friction of geopolitics, of military tensions and military conflicts, is a successful empire, successful civilization. Because trade is really, really important. It's a kind of a financial freedom. So it's nice when in a digital age, we build systems like Shopify that allows you to exercise that financial freedom by buying stuff, selling stuff, create the market at scale in the digital world. Sign up for a $1 per month trial period at shopify.com/Lex. That's all lowercase. Go to shopify.com/Lex to take your business to the next level today. This episode is also brought to you by AG1, an all-in-one daily drink to support better health and peak performance. Because I mentioned peak performance, I'm reminded of Nietzsche. And the book I read maybe freshman, maybe sophomore year in college, Thus Spoke Zarathustra. It's been forever. I've been reading summaries of Nietzsche, way more than Nietzsche directly since college. That's one of the worries I have with AI, is the summaries, the talking about the talking about the talking is so damn efficient and fun and easy and even insightful that you don't want to go to the original sources because it's a lot of work. But you must, of course, if you want to understand. As the meme goes, but have you been there? That never gets old. And anyway, I think about that with some of the classics, but even some of the 20th century, 19th century works, you want to read Marx directly. You want to read Nietzsche directly. You want to read Sigmund Freud and Carl Jung directly. Because, of course, there is great books about them, about their ideas, summarizing their ideas, elaborating on their ideas, putting them in the proper context. But there's nothing quite like reading it directly. But anyway, I brought that up because in Thus Spoke Zarathustra, there's the pursuit of peak human potential. And we in the West, on the health front, have at times taken that to an almost ridiculous place. I think it's still really useful. But sometimes it's also useful to fuck off a bit, to relax a bit, and not care. Funny enough, AG1 helps me in a certain kind of way. Relax and not care. I got my nutrition handled. I can do all kinds of crazy physical stuff, mental stuff, because I'm drinking AG1. They'll give you a 1-month supply of fish oil when you sign up at drinkag1.com/Lex. This is a Lex Friedman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Janna Levin. I should say that you sent me a message about not starting early in the morning, and that made me feel like we're kindred spirits.
Yeah.
You wrote to me, when the great physicist Sidney Coleman was asked to attend a 9 a.m. meeting, his reply was, "I can't stay up that late."
Yeah.
So,
classic. Sidney was beloved.
I think all the best thoughts, honestly,
Mhm.
maybe the worst thoughts too, are all come at night. There's something about the night. Maybe it's the silence.
Mhm.
Maybe it's the peace all around. Maybe it's the darkness, and you could be with yourself and you could think deeply.
I feel like they're stolen hours in the middle of the night because it's not busy. Your gadgets aren't pinging. There's really no pressure to do anything, but I'm often awake in the middle of the night. And so it's sort of like these extra hours of the day. I think we were exchanging messages at 4 a.m.
Okay. So in that way, in many other ways, we're kindred spirits.
Mm.
So let's go. In one of the coolest objects in the universe, black holes, what are they? And maybe even a good way to start is to talk about how are they formed?
Yeah. In a way, people often confuse how they're formed with the concept of the black hole in the first place. So when black holes were first proposed, Einstein was very surprised that such a solution could be found so quickly, but he really thought nature would protect us from their formation. And then nature thinks of a way. Nature thinks of a way to make these crazy objects, which is to kill off a few stars. But then I think that there's a confusion that dead stars, these very, very massive stars that die, are synonymous with the phenomenon of black hole. And it's really not the case. Black holes are more general and more fundamental than just the death state of a star. But even the history of how people realize that stars could form black holes is quite fascinating because the entire idea really just started as a thought experiment. And if you think of it's 1915, 1916, when Einstein fully describes relativity in a way that's the canonical formulation. It was a lot of changing back and forth before then. And it's World War I, and he gets a message from the Eastern Front from a friend of his, Carl Schwarzschild, who solved Einstein's equations, between sitting in the trenches and like cannon fire. It was joked that he was calculating ballistic trajectories. He's also perusing the proceedings of the Prussian Academy of Sciences, as you do. And he was an astronomer who had enlisted in his 40s. And he finds this really remarkable solution to Einstein's equations. And it's the first exact solution. He doesn't call it a black hole. It's not called a black hole for decades. But what I love about what Schwarzschild did is it's a thought experiment. It's not about observations. It's not about making these things in nature. It's really just about the idea. He sets up this completely untenable situation. He says, imagine I crush all the mass of a star to a point. Don't ask how that's done, because that's really absurd. But let's just pretend, and let's just imagine that that's a scenario. And then he wants to decide what happens to space-time if I set up this confounding but somehow very simple scenario. And really what Einstein's equations were telling everybody at the time was that matter and energy curve space and time, and then curved space-time tells matter and energy how to fall once the space-time's shaped. So he finds this beautiful solution. And the most amazing thing about his solution is he finds this demarcation, which is the event horizon, which is the region beyond which not even light can escape. And if you were to ask me today, all these over 100 years later, I would say that is the black hole. The black hole is not the mass crushed to a point. The black hole is the event horizon. And the event horizon is really just a point in spacetime or a region in spacetime. It's actually, in this case, a surface in spacetime. And it marks a separation in events, which is why it's called an event horizon. Everything outside is causally separated from the inside insofar as what's inside the event horizon can't affect events outside. What's outside can affect events inside. I can throw a probe into a black hole and cause something to happen on the inside. But the opposite isn't true. Somebody who fell in can't send a probe out. And this one-way aspect really is what's profound about the black hole. Sometimes we talk about the black holes being nothing because at the event horizon, there's really nothing there. Sometimes when we think about black holes, we want to imagine a really dense, dead star. But if you go up to the event horizon, it's an empty region of space-time. It's more of a place than it is a thing. And Einstein found this fascinating. He helped get the work published, but he really didn't think these would form in nature. I doubt Carl Schwarzschild did either. I think they thought they were solving theoretical, mathematical problems, but not describing this, what turned out to be the end state of gravitational collapse.
And maybe the purpose of the thought experiment was to find the limitations of the theory. So you find the most extreme versions in order to understand where it breaks down.
Yeah.
And it just so happens in this case that might actually predict these extreme kinds of objects.
It does both. So it also describes the sun from far away. So the same solution does a great job helping us understand the Earth's orbit around the sun. It's incredible. It does a great job. It's almost overkill. You don't really need to be that precise as relativity. And yes, it predicts the phenomenon of black holes, but doesn't really explain how nature would form them. But then it also, on top of that, does signal the breakdown of the theory. I mean, you're quite right about that. It actually says, oh man, but you go all the way towards the center and yeah, this doesn't sound right anymore. Sometimes I liken it to, it's like a dying man marking in the dirt that something's gone wrong here. Right, it's signaling that there's some culprit, there's something wrong in the theory, and even Roger Penrose, who did this general work trying to understand the formation of black holes from gravitational collapse, he thought, oh yeah, there's a singularity that's inevitable. It's there's no way around it once you form a black hole. But he said this is probably just a shortcoming of the fact that we've forgotten to include quantum mechanics. And that when we do, we'll understand this differently.
So according to him, the closer you get to the singularity, the more quantum mechanics comes into play, and therefore there's no singularity, there's something else.
I think everybody would say that. I think everybody would say the closer you get to the singularity, for sure you have to include quantum mechanics. You just can't consistently talk about magnifying such small scales, having such enormous ruptures and curvatures and energy scales and not include quantum mechanics. That's just inconsistent with the world as we understand it.
So you've described the brain-breaking idea that a black hole is not so much a super dense matter as it's sometimes described, but it's more akin to, a region of space-time, but even more so just nothing.
Yeah.
It's nothing. That's the thing you seem to like to say.
I do like to say that black holes are no thing. They're nothing.
Okay, so what does that mean?
And that's what I mean. That's the more profound aspect of the black hole. So you asked originally, how do they form? And I think that even when you try to form them in messy astrophysical systems, there's still nothing at the end of the day left behind. And this was a very big surprise. Even though Einstein accepted that this was a true prediction, he didn't think that they'd be made. And it was quite astounding that people like Oppenheimer, actually it's probably Oppenheimer's most important theoretical work, who are thinking about nuclear physics and quantum mechanics, but in the context of these kind of utopian questions. Why do stars shine? Why is the sun radiant and hot and this amazing source of light? And it was people like Oppenheimer who began to ask the question, well, could stars collapse to form black holes? Could they become so dense that eventually not even light would escape? And that's why I think people think that black holes are these dense objects. That's often how it's described. But actually what happens, these very massive stars, they're burning thermonuclear fuel. They're earthfuls of thermonuclear fuel they're burning. And emitting energy in E equals mc squared energy. So it's fusing, it's a fusion bomb. It's a constantly going thermonuclear bomb. And eventually it's going to run out of fuel. It's going to run out of hydrogen, helium, stuff to fuse. It hits an iron core. Iron, to go past iron with fusion is actually energetically expensive. So it's no longer going to do that so easily. So suddenly it's run out of fuel. And if the star is very, very, very massive, much more massive than our sun, maybe 20, 30 times the mass of our sun, it'll collapse under its own weight. And that collapse is incredibly fast and dramatic, and it creates a shock wave. So that's the supernova explosion. So a lot of these, they rebound because once they crunch, they've reached a new critical capacity where they can reignite to higher elements, heavier elements, and that sets off a bomb, essentially. So the star explodes, helpfully, because that's why you and I are here, because stars send their material back out into space, and you and I get to be made of carbon and oxygen and all this good stuff. We're not just hydrogen. So the suns do that for us. And then what's left sometimes ends at a neutron star, which is a very cool object, very fascinating object, super dense, but bigger than a black hole, meaning it's not compact enough to become a black hole. It's an actual thing. A neutron star is a real thing. It's like a giant neutron. Literally, electrons get jammed into the protons and make this giant nucleus and this superconducting matter. Very strange, amazing objects. But if it's heavier than that, the core, and that's heavier than twice the mass of the sun, it will become a black hole. And Oppenheimer wrote this beautiful paper in 1939 with his student saying that they believed that the end state of gravitational collapse is actually a black hole. This is stunning and really a visionary conclusion. Now, the paper is published the same day the Nazis advance on Poland. And so it does not get a lot of fanfare in the newspapers.
Yeah, we think there's a lot of drama today on social media. Imagine that.
Yeah.
Like, here's a guy who predicts how actually in nature would be the formation of this most radical of object that broke even Einstein's brain, while one of the most evil, if not the most evil humans in history is starting the first steps of a global war.
What I also love about that lesson is how agnostic science is.
Yeah.
Because he was asking these utopian questions, as were other people of the time, about the nuclear physics in stars. You might know this play, Copenhagen, by Michael Frayn. There's this line that he attributes to Bohr. And Bohr was the great thinker of early foundations of quantum mechanics, Danish physicist, where Bohr says to his wife, nobody's thought of a way to kill people using quantum mechanics. Now, of course, then there's the nuclear bomb. And what I love about this was the pressure scientists were under to do something with this nuclear physics and to enter this race over a nuclear weapon. But really, at the same time, 1939, really, Oppenheimer's thinking about black holes. There's even a small line in Chris Nolan's film. It's very hard to catch. There's a reference to it in the film where they're sort of joking, well, I guess nobody's going to pay attention to your paper now, because of the Nazi advance on Poland.
That's the other remarkable thing about Oppenheimer is he's also a central figure in the construction of the bomb.
Right.
So it's theory and experiment clashing together with the geopolitics.
Exactly. So, of course, Oppenheimer, now known as the father of the atomic bomb, he talks about destroyers of worlds. But it's the same technology. And that's what I mean by science is agnostic, right? It's the same technology, overcoming a critical mass, igniting thermonuclear fusion. Eventually, there was a fission. The original bomb was a fission bomb. And fission was first shown by Lise Meitner, who showed that a certain uranium, when you bombarded it with protons, broke into smaller pieces that were less than the uranium, right? So some of that mass, that E equals mc squared energy, had escaped. And it was the first kind of concrete demonstration of this, Einstein's most famous equation. So all of this comes together. But the story of, they still weren't called black holes. This is 1939. And they had these very long-winded ways of describing the end state, the catastrophic end state of gravitational collapse. But what you have to imagine is as this star collapses, so what's the sun? The sun's 1.5 million kilometers across. So imagine a star much bigger than the sun, much bigger radius, and it's so heavy it collapses, it's supernovas. What's left is still maybe 10 times the mass of the sun, just what's left in that core. And it continues to collapse. And when that reaches about 60 kilometers across, like just imagine 10 times the mass of the sun, city-sized. That is a really dense object. And now the black hole essentially has begun to form, meaning the curve in space-time is so tremendous that not even light can escape. The event horizon forms, but the event horizon is almost imprinted on the space-time because the star can't sit there in that dense state any more than it can race outward at the speed of light, because even light is forced to rain inwards. So the star continues to fall, and that's the magic part. The star leaves the event horizon behind, and it continues to fall, and it falls into the interior of the black hole. Where it goes, nobody really knows, but it's gone from sight. It goes dark. There's this quote by John Wheeler, who's like granddaddy of American relativity, and he has a line that's something to the effect, the star, like the Cheshire cat, fades from view. One leaves behind only its grin, the other only its gravitational attraction. And he was giving a lecture. It's actually above Tom's Restaurant, from Seinfeld near Columbia in New York.
Nice.
There was a place there still is a place there where people were giving lectures about astrophysics, and it's 1967. Wheeler is exhaustively saying this loaded term, the end state of catastrophic gravitational collapse. And rumor is that someone shouts from the back row, well, how about black hole? And apparently he then foists this term on the world. Wheeler had a way of doing that.
Well, I love terms like that. Big Bang, black hole.
Mm-hmm.
There's it's just pointing out the elephant in the room and calling it an elephant. It is a black hole.
Mm-hmm.
That's a pretty accurate and deep description. I just wanted to point out that just looking for the first time at the 1939 paper from Oppenheimer, it's like 2 pages. It's like 3 pages.
Oh, yeah, it's gorgeous.
The simplicity of some of these, that's so gangster. Just revolutionize all of physics with this. Einstein did that multiple times in a single year.
Mm-hmm.
When all thermonuclear sources of energy are exhausted, a sufficiently heavy star will collapse. That's an opener.
Mm-hmm.
Unless fission due to rotation, the radiation of mass, or the blowing off of mass by radiation reduce the star's mass to orders of that of the sun, this contraction will continue indefinitely.
Mm-hmm.
And it goes on that way.
Yeah. Now, I have to say that Wheeler, who actually coins the term black hole, gives Oppenheimer quite a terrible time about this. He thinks he's wrong. And they entered what has sometimes been described as kind of a bitter, I don't know if you would actually say feud, but there were bad feelings. And Wheeler actually spent decades saying Oppenheimer was wrong. And eventually, with his computer work, that early work that Wheeler was doing with computers, when he was also trying to understand nuclear weapons, and in peacetime found themselves returning again to these astrophysical questions, decided that actually Oppenheimer had been right. He thought it was too simplistic, too idealized a setup that they had used, and that if you looked at something that was more realistic and more complicated, that it just would go away. And in fact, he draws the opposite conclusion. And there's a story that Oppenheimer was sitting outside of the auditorium when Wheeler was coming forth with his declaration that, in fact, black holes were the likely end state of gravitational collapse for very, very heavy stars. And when asked about it, Oppenheimer sort of said, well, I've moved on to other things.
Because you've written in many places about the human beings behind the science. I have to ask you about this, about nuclear weapons. Whereas the greatest of physicists coming together to create this most terrifying and powerful of a technology. And now I get to talk to world leaders for whom this technology is part of the tools that is used perhaps implicitly on the chessboard of geopolitics. What can you say as a person who's a physicist and who have studied the physicists and written about the physicists, the humans behind this, about this moment in human history when physicists came together and created this weapon that's powerful enough to destroy all of human civilization?
I think it's an excruciating moment in the history of science. And people talk about Heisenberg, who stayed in Germany and worked for the Nazis in their own attempt to build the bomb. There was this kind of hopeful talk that maybe Heisenberg had intentionally derailed the nuclear weapons program, but I think that's been largely discredited, that he would have made the bomb, had he not made some really kind of simple errors in his original estimates about how much material would be required or how they would get over the energy barriers. And that's a terrifying thought. I don't know that any of us can really put ourselves in that position of imagining that we're faced with that quandary, having to take the initiative to participate in thinking of a way that quantum mechanics can kill people, and then making the bomb. I think overwhelmingly physicists today feel we should not continue in the proliferation of nuclear weapons. Very few theoretical physicists want to see this continue.
That moment in history The Soviet Union had incredible scientists. Nazi Germany had incredible scientists. And the United States had incredible scientists. And it's very easy to imagine that one of those three would have created the bomb first, not the United States.
Yes.
And how different would the world be? The game theory of that. I think, say the probability is 33% that it was the United States. If the Soviet Union had the bomb, I think they would have used it in a much more terrifying way in the European theater and maybe turn on the United States. And obviously with Hitler, he would have used it. I think there's no question he would have used it to kill hundreds of millions of people.
In the game theory version, this was the least harmful outcome. Yes. But there is no outcome with no bomb that any game theorist would, I think, would play.
But I think if we just remove the geopolitics and the ideology and the evil dictators, all of those people are just scientists. I think they don't necessarily even think about the ideology. And it's a deep lesson about the connection between great science and the annoying, sometimes evil politicians that use that science for means that are either good or bad. And the scientists perhaps don't. Boy, do they even have control of how that science is used? It's hard.
They don't have control, right? Once it's made, it's no longer scientific reasoning that dictates the use or it's restraint. But I will say that I do believe that it wasn't a 1/3 down the line, because America was different. And I think that's something we have to think about right now in this particular climate. So many scientists fled here. They fled to here. Americans weren't fleeing to Nazi Germany. They came here and they were motivated by, it's more than a patriotism, it was it was a patriotism, obviously, but it was sort of more than that. It was really understanding the threat of Europe, what was going on in Europe, and what that life, how quickly it turned, how quickly this free-spirited Berlin culture, was suddenly in this repressive and terrifying regime. So I think that it was a much higher chance that it happened here in America.
Yeah, and there's something about the American system, it's cliche to say, but the freedom, all the different individual freedoms that enable a very vibrant, at its best, a very vibrant scientific community. And that's really exciting.
Absolutely.
To scientists. And it's very valuable to maintain that.
Right.
The vibrancy of the debate, of the funding those mechanisms.
Absolutely. The world flocked here. And that won't be the case if we no longer have intellectual freedom.
Yeah, there's something interesting to think about. The tension, the Cold War between China and the United States in the 21st century, some of those same questions, some of those ideas will rise up again. And we want to make sure that there's a vibrant, free exchange of scientific ideas. I believe most Nobel Prizes come from the United States, right?
Oh, yeah, I don't have the number, but
it's disproportionately so.
Disproportionately so. In fact, a lot of them from particle physics came from the Bronx. And they were European immigrants.
How do we explain this?
Fled Europe precisely because of the geopolitics we're describing.
Yeah.
And so instead of being Nobel Prize winners from the Soviet Union or from the Eastern Bloc, they were from the Bronx.
And that's the thing you write about, and we'll return to time and time again, that, science is done by humans, and some of those humans are fascinating. There's tensions, there's battles, some are loners, some are great collaborators, some are tormented, some are easygoing, all this kind of stuff. And that's the beautiful thing about it. We forget sometimes is it's humans, and humans are messy and complicated and beautiful and all of that.
Yeah.
So what were we talking about? Oh,
the stars collapsing.
Okay. So can we just return to the collapse of a star that forms a black hole? At which point does the super dense thing become nothing? If we can just linger on this concept.
Yeah. So if I were falling into a black hole and I tried really fast, right as I crossed this empty region, but this demarcation, I happened to know where it was. I calculated, because there's no line there. There's no sign that it's there. There's no signpost. I could emit a little light pulse and try to send it outward exactly at the event horizon. So it's racing outward at the speed of light. It can hover there because from my perspective, it's very strange. The space-time is like a waterfall raining in, and I'm being dragged in with that waterfall. I can't stop at the event horizon. It comes, it goes. It's behind me really quickly. That light beam can try to sit there because it's like a fish swimming against the Niagara, swimming against a waterfall.
It's like stuck there.
But it's like stuck there. And so that's one way you can have a little signpost. If you fly by, you think it's moving at the speed of light. It flies past you at the speed of light, but it's sitting right there at the event horizon.
So you're falling back, cross the event horizon, right at that point, you shoot outwards a photon.
Yes.
And it's just stuck there.
It just gets stuck there. Now, it's very unstable. So the star can't sit there is the point. It just can't. So it rains inward with this waterfall. But from the outside, all we should ever really care about is the event horizon, because I can't know what happens to it. It could be pure matter and antimatter thrown together, which annihilates into photons on the inside and loses all its mass into the energy of light. Won't matter to me because I can't know anything about what happened on the inside.
Okay, can we just linger on this? So what models do we have about what happens on the inside of the black hole at that moment? So I guess that one of the intuitions, one of the big reminders that you're giving to us is hey, we know very little about what can happen on the inside of a black hole. And that's why we have to be careful about it's better to think about the black hole as an event horizon. But what can we know and what do we know about the physics of space-time inside the black hole?
I don't mind being incautious about thinking about what the math tells us. So I'm not such an observer, right? I'm very theoretical in my work. It's really pen on paper a lot. These are thought experiments that I think we can perform and contemplate. Whether or not we'll ever know is another question. And so one of the most beautiful things that we suspect happens on the inside of a black hole is that space and time, in some sense, swap places. So while I'm on the outside of the black hole, let's say I'm in a nice, comfortable space station, this black hole is maybe 10 times the mass of the sun, 60 kilometers across. I could be 100 kilometers out. That's very, very close. Orbiting quite safely. No big deal, hanging out. I don't bug the black hole. Black hole doesn't bug me. It won't suck me up like a vacuum or anything crazy. But my astronaut friend jumps in. As they cross the event horizon, what I'm calling space, I'm looking on the outside at this spherical shadow of the black hole cast by maybe light around it. It's a shadow because everything gets too close, falls in. It's just this just contrast against a bright sky. I think, there's a center of a sphere. And in the center of the sphere is the singularity. It's a point in space from my perspective. But from the perspective of the astronaut who falls in, it's actually a point in time. So their notions of space and time have rotated so completely that what I'm calling a direction in space towards the center of the black hole, like the center of a physical sphere, they're going to tell me, well, they can't tell me, but they're going to come to the conclusion, oh, no, that's not a location in space. That's a location in time. In other words, the singularity ends up in their future, and they can no more avoid the singularity than they can avoid time coming their way. So there's no shenanigans you can do once you're inside the black hole to try to skirt it, the singularity. You can't set yourself up in orbit around it. You can't try to fire rockets and stay away from it because it's in your future. And there's an inevitable moment when you will hit it. Usually for a stellar mass black hole, we think it's microseconds.
Microseconds to get from the event horizon to the
singularity.
To the singularity. Oh boy. So that's describing from your astronaut friend's perspective.
Yes, from their perspective, the singularity's in their future.
But from your perspective, what do you see when your friend falls into the black hole and you're chilling outside and watching?
So one way to think about this is to think that as you're approaching the black hole, the astronaut's space-time is rotating relative to your space-time. So let's say right now, my left is your right. We're not shocked by the fact that there's this relativity in left and right. It's completely understood. And I can perform a spatial rotation to align my left with your left. Right now, I've completely rotated left out, right? If I just want to draw a kind of compass diagram, not a compass diagram, but at the top of maps, there's a north, south, east, west. But now time is up, down, and one direction of space is, let's say, east, west. As you approach the black hole, it's as though you're rotating in space-time, is one way of thinking about it. So what is the effect of that? The effect of that is as this astronaut gets closer and closer to the event horizon, part of their space is rotated into my time, and part of their time is rotated into my space. So in other words, their clocks seem to be less aligned with my time. And the overall effect is that their time seems to dilate. The spacing between ticks on the clock of their watch, let's say, on the face of their watch, is elongated, dilated relative to mine. And it seems to me that their watches are running slowly, even though they were made in the same factory as mine. They were both synchronized beautifully, and they're excellent Swiss watches. It seems as though time is elapsing more slowly for my companion. And likewise, for them, it seems like mine's going really fast. So years could elapse in my space station. My plants come and go. They die. I age faster. I've got gray hair. And they're falling in, and it's been minutes in their frame of reference. Flowers in their little rocket ship haven't rotted. They don't have gray hair. Their biological clocks have slowed down relative to ours. Eventually, at the event horizon, it's so extreme, it's so slow, it's as though their clocks have stopped altogether from my point of view. And that's to say that it's as though their time is completely rotated into my space. And this is connected with the idea that inside the black hole, space and time have switched places. So I might see them hover there for millennia. Other astronauts could be born on my space station. Generations could be populated there watching this poor astronaut never fall in.
So basically, the time almost comes to a standstill, but they do fall in.
Right. They do fall in eventually. Now, that's because they have some mass of their own.
Yeah.
So they're not a perfectly light particle. And so they deform the event horizon a little bit. You will actually see the event horizon bobble and absorb the astronaut. So in some finite time, the astronaut will actually fall in.
So it's like this weird space-time bubble that we have around us. And then there's a very big space-time curvature bubble thing from the black hole, and there's a nice swirly type situation going on. That's how you get sucked up.
Yeah.
So if you're a perfect, infinitely small particle, you would just
take longer and longer.
And probably just be stuck there or something. But no, there's quantum mechanics.
Eventually you'll fall in. Any perturbation will only go one way. It's unstable in one direction, in one direction only. But it's really important to remember that from the point of view of the astronaut, not much time has passed at all. You just sail right across as far as you're concerned, and nothing dramatic happens there. You might not even realize you've come to the event horizon. You might not even realize you've crossed the event horizon because there's nothing there, right? This is an empty region of space-time. There's no marker to tell you you've reached this very dangerous point of no return. You can fire your rockets like hell when you're on the outside and maybe even escape, right? But once you get to that point, there's no amount of energy. All the energy in the universe will not save you from this demise.
There's different size black holes. And maybe can we talk about the experience that you have falling into a black hole depending on what the size of the black hole is?
Yeah.
Because as I understand, if the bigger it is, the less drastic the experience of falling into it.
Yeah, that might surprise people.
Yeah.
The bigger it is, the less noticeable it is that you've crossed the event horizon. One way to think about it is curvature is less noticeable the bigger it is. So if I'm standing on a basketball, I'm very aware I'm balancing on a curved surface. My 2 feet are in different locations, and I really notice. But on the Earth, you actually have to be kind of clever to deduce that the Earth is curved. The bigger the planet, the less you're going to notice the curvature, the global curvature. And it's the same thing with a black hole. A huge, huge black hole, it just kind of feels like just flat. You don't really notice.
I'm trying to figure out how because if you don't notice,
And there's nothing there.
but the physics is weird.
In your frame of reference.
No.
Well, so another cool thing. So I like to dispel myths.
Yeah.
Do you need a minute? You're holding your head.
There's a sense like you should be able to know when you're inside of a black hole, when you've crossed the event horizon. But no, from your frame of reference, you might not be able to know.
Yeah, at first, at least, you might not realize what's happened. There are some hints. For instance, black holes are dark from the outside, but they're not necessarily dark on the inside. So this is a kind of fascinating that your experience could be that it's quite bright inside the black hole because all the light from the galaxy can be shining in behind you and it's focusing down because you're all approaching this really focused region in the interior. And so you actually see a bright white flash of light as you approach the singularity. I kind of I joke that it's like a near-death experience. You see the light at the end of the tunnel. So you would see millennia pass on Earth. You could see the evolution of the entire galaxy, one big bright flash of light. So it's like a near-death experience, but it's definitely a total death experience.
It goes pretty fast, but you looking out, everything's going super fast.
Yeah. The clocks on the Earth, on the space station, seem to be progressing very rapidly relative to yours. The light can catch up to you, and you get this bright beam of light as you see the evolution of the galaxy unfold. And it sort of depends on the size of the black hole and how long you have to hang around. The bigger the black hole, the longer it takes you to expire in the center.
Obviously, the human sensory system, we're not able to process that information correctly.
Right. It would be a microsecond that would be too fast.
Yeah, but it would be so cool to get that information.
But a big black hole, you could actually, hang around for some months.
So yeah, how are small black holes versus supermassive black holes formed? Just so people can kind of load that in. Is it always a star?
No. So this is also why it's important to think of black holes more abstractly. They are something very profound in the universe, and there are probably multiple ways to make black holes. Making them with stars is most plentiful. There could be hundreds of millions, maybe even a billion black holes in our Milky Way galaxy alone. That many stars. It's only about 1% of stars that will end their lives in a death state that is a black hole. But we now see, and this was really quite a surprise, that there are supermassive black holes. They're billions or even hundreds of billions of times the mass of the sun. And millions to tens of billions, maybe even hundreds of billions. So extremely massive. We don't think that the universe has had enough time to make them from stars that just merge. We know that 2 black holes can merge and make a bigger black hole, and then those can merge and make a bigger black hole. But we don't think there's been enough time for that. So it's suspected that they're formed very early, maybe even a few hundred million years after the Big Bang, and that they're formed directly by collapsing out of primordial stuff. That there's a direct collapse right into the black hole.
So like in the very early universe, these are primordial black holes from the
They're
stars
different.
Not quite.
Yeah.
Wait, how do you get from that soup black holes right away?
Right. So it's odd, but it's weirdly easier to make a big black hole out of something that's just the density of air, if it's really, really as big as what we're talking about. So in some sense, if they're just allowed to directly collapse very early in the universe's history, they can do that more easily. And it's so much so that we think that there's one of these supermassive black holes in the center of every galaxy.
Mm-hmm.
So they're not rare, and we know where they are. They're in the nuclei of galaxies. So they're bound to the very early formation of entire galaxies in a really surprising and deeply connected way.
I wonder if the chicken or the egg, is it like how critical, how essential are the supermassive black holes to the formation of galaxies?
Hmm. Yeah, I mean, it's ongoing, right? It's ongoing. Which came first, the
Yeah.
black hole or the galaxy? Probably big early stars, which were just made out of hydrogen and helium from the Big Bang. There wasn't anything else, not much of anything else. Those early stars were forming, and then maybe the black holes and kind of the galaxies were like these gassy clouds around them. But there's probably a deep relationship between the black hole powering jets, these jets blowing material out of the galaxy that shaped galaxies, maybe kind of curbed their growth. And so I think the mechanisms are still ongoing attempts to understand exactly the ordering of these things.
Can we get back to space-time? Just going back to the beginning of the 20th century, how do you imagine space-time? How do we as human beings supposed to visualize and think about space-time
Mm.
where, time is just another dimension in this 4D space
Mm.
that combines space and time? Because we've been talking about morphing in all kinds of different ways, the curvature of space-time. Like, how are we supposed to conceive of it? How do you think of it?
Yeah.
Time is just another dimension.
There are different ways we can think about it. We can imagine drawing a map of space and treating time as another direction in that map. But we're limited because as three-dimensional beings, we can't really draw 4 dimensions, which is what I'd require. 3 spatial, because I'm pretty sure there's at least 3. I think there's probably more. But I'm happy just talking about the large dimensions, the 3 we see up, down, right? East, west, north, south, three spatial dimensions. And time is the 4th. Nobody can really visualize it. But we know mathematically how to unpack it on paper. I can mathematically suppress one of the spatial dimensions, and then I can draw it pretty well. Now, the problem is that we'd call it a Euclidean spacetime. A Euclidean spacetime is when all the dimensions are orthogonal and are treated equally. Time is not another Euclidean dimension. It's actually a Minkowskian spacetime. But it means that the spacetime, we're misrepresenting it when we draw it, but we're misrepresenting it in a way that we deeply understand. I can give you an example. The Earth, I can project onto a flat sheet of paper. I am now misrepresenting a map of the Earth. And I know that, but I understand the rules for how to add distances on this misrepresentation because the Earth is not a flat sheet of paper. It's a sphere. And as long as I understand the rules for how I get from the North Pole to the South Pole, that I'm moving along really a great arc, and I understand that the distance is not the distance I would measure on a flat sheet of paper, then I can do a really great job with a map and understanding the rules of addition, multiplication, and the geometries, not the geometry of a flat sheet of paper. I can do the same thing with space-time. I can draw it on a flat sheet of paper, but I know that it's not actually a flat Euclidean space. And so my rules for measuring distances are different than the rules I would use that, for instance, Cartesian rules of geometry. I would know to use the correct rules for Minkowski spacetime, and that will allow me to calculate how long time has elapsed, which is now a kind of a length, a space-time length on my map between 2 relative observers, and I will get the correct answer. But only if I use these different rules.
So then what does, according to general relativity, does objects with mass do to the space-time?
Right, exactly. So Einstein struggled for this completely general theory, not a specific solution like a black hole or an expanding space-time or galaxies make lenses, or those are all solutions. That's why what he did was so enormous. It's an entire paradigm that says over here is matter and energy. I'm going to call that the right-hand side of the equation. Everything on the right-hand side of Einstein's equations is how matter and energy are distributed in spacetime. On the left-hand side, tells you how space and time deform in response to that matter and energy. And it can be impossible to solve some of those equations. What was so amazing about what Schwarzschild did is he found this very elegant, simple solution within like a month of reading this final formulation. But Einstein didn't go through and try to find all the solutions. He sort of gave it to us, right? He shared this, and then lots of people since have been scrambling to try to, I can predict the curvature of the spacetime if I tell you how the matter and energy is laid out. If it's all compact in a spherical system like a sun or even a black hole, I can understand the curves in the spacetime around it. I can solve for the shape of the spacetime. I can also say, well, what if the universe is full of gas or light and it's all kind of uniform everywhere? And I'll find a different and equally surprising solution, which is that the universe would expand in response to that it's not static, that the distances between galaxies would grow. This was a huge surprise to Einstein. So all of these consequences of his theory, came with revelations that were not at all obvious when he first wrote down the general theory.
And he was afraid to take the consequences of that theory seriously, which is
Often.
The theory itself in its scope and grandeur and power is scary, so I can understand. Then there's, the edges of the theory where it falls apart, the consequences of the theory that are extreme. It's hard to take seriously. So you can sort of empathize.
Yeah, he very much resisted the expansion. So if you think about 1905, when he's writing these sequence of unbelievable papers as a 25-year-old who can't get a job, as a physicist, and he writes all of these remarkable papers on relativity and quantum mechanics. And then even in 1915-16, he does not know that there are other galaxies out there. This was not known. People had mused about it. There were these kind of smudges on the sky that people contemplated. What if there are other island universes? Going back to Kant, thought about this. But it wasn't until Hubble, it really wasn't until the late 20s, that it's confirmed that there are other galaxies.
Wow.
Yeah.
And he didn't, obviously, there's so much we think of now that he didn't think of. So there's no Big Bang.
Right.
Static universe.
But these are all connected.
Wow. Yeah. So he's operating on very little information.
Very little information. That's absolutely true. Actually, one of the things I like to point out is the idea of relativity was foisted on people in this kind of cultural way. But there's many ways in which you could call it a theory of absolutism. And the way Einstein got there with so little information is by adhering to certain very strict absolutes, like the absolute limit of the speed of light and the absolute constancy of the speed of light, which was completely bizarre when it was first discovered. Really, that was observed. There were experiments trying to figure out what would the relative speed of light be? It's really only massless particles have this property that they have an absolute speed. And if you think about it, it's incredibly strange.
Yeah, it's really
incredibly strange.
And then so from a theoretical perspective, he takes that seriously.
He takes it very seriously, and everyone else is trying to come up with models to make it go away, to make the speed of light be a little bit more reasonable, like everything else in the universe. If I run at a car, two cars coming at each other, they're coming at each other faster than if one of them stops. It's really a basic observation of reality, right? Here, this is saying that if I'm racing at a light beam and you're standing still relative to the source, we'll measure the same exact speed of light. Very strange. And he gets to relativity by saying, well, what's speed? Speed is distance, it's space over time. It's how far you travel. It's the space you travel in a certain duration of time. And he said, well, I bet something must be wrong then with space and time. So this is an enormous leap. He's willing to give up the absolute character of space and time in favor of keeping the speed of light constant.
How was he able to intuit a world of curved space-time? I think it's like one of the most special leaps in human history, right? Because you're
It's amazing.
like, it's very, very, very difficult to make that kind of leap.
I'll tell you, it took me, I think, a long time I can't say this is how he got there exactly. It's not as though I studied the historical accounts or his description of his internal states. This is more having learned the subject, how I try to tell people how to get there in a few short steps. One is to start with the equivalence principle, which he called the happiest thought of his life. And the equivalence principle comes pretty early on in his thinking. And it starts with something like this. Like right now, I think I'm feeling gravity because I'm sitting in this chair and I feel the pressure of the chair and it's stopping me from falling. And lie down in a bed and I feel heavy on the bed. And I think of that as gravity. And Einstein has a beautiful ability to remove all of these extraneous factors, including atoms. So let's imagine instead that you're in an elevator and you feel heavy on your feet because the floor of the elevator is resisting your fall. But I want to remove the elevator. What does the elevator have to do with fundamental properties of gravity? So I cut the cable. Now I'm falling, but the elevator is falling at the same rate as me. So now I'm floating in the elevator. And if this happened to me, if I woke up in this state of falling or floating in the elevator, I might not know if I was in empty space, just floating, or if I was falling around the earth. They're equivalent situations. I would not be able to tell the difference. When I get rid of the elevator in this way by cutting the cable, I'm actually experiencing weightlessness. And that weightlessness is the purest experience of gravity. And so this idea of falling is actually fundamental. It's how we talk about it all the time. The Earth is in a free fall around the sun. It's actually falling. It's not firing engines, right? It's just falling all the time, but it's just cruising so fast.
So actually, yeah, oh God, you said so many profound things there. So one of them is really one of the ways to experience space-time is to be falling.
To be falling. That is the purest experience of gravity. The experience of gravity, unfettered, uninterrupted by atoms, is weightlessness.
Yeah.
That observation, no, it has an unhappy ending, the elevator story,
Yeah.
right? Because of atoms again. That's the fault of the atoms in your body interacting electromagnetically with the crust of the earth or the bottom of the building or whatever it is. But this period of free fall, so the first observation is that is the purest experience of gravity. Now I can convince you that things fall along curved paths because I could take, a pen, and if I throw it, we both know it's going to follow an arc. And it's going to follow an arc until atoms interfere again and it hits the ground. But while it's in free fall, experiencing gravity at its purest, what the Einsteinian description would say is it is following the natural curve in space-time inscribed by the Earth. So the Earth's mass and shape curves the paths in space, and then those curvatures tell you how to fall, the paths along which you should fall when you're falling freely. And so the Earth has found itself on a free fall that happens to be a closed circle, but it's actually falling. The International Space Station uses this principle all the time. They get the space station up there, and then they turn off the engines. Can you imagine how expensive it would be if they had to fuel that thing at all times, right? They turn off the engines. They're just falling.
Yeah, they're falling.
And they're not that far up. There are certainly people sometimes say, oh, they're so far away, they don't feel gravity. Oh, absolutely. If you stopped the space station, it's going like 17,500 miles an hour, something like that. If you were to stop that, it would drop like a stone right to the earth. So they're in a state of constant freefall, and they're falling along a curved path. And that curved path is a result of curving space-time.
And that particular curved path is calculated in such a way that it curves onto itself. So you're orbiting.
Right. So it has to be cruising at a certain speed. So once you get it at that cruising speed, you turn off the engines.
But yeah, to be able to visualize at the beginning of the 20th century, that free falling in curved space-time.
Mm-hmm.
Boy, the human mind is capable of things. I mean, some of that is constructing thought experiments that collide with our understanding of reality.
Mm.
Maybe in the collisions and the contradictions, you try to think of extreme thought experiments that exacerbate that contradiction and see, like, okay, what is there another model that can incorporate this? But to be able to do that, I mean, it's kind of inspiring because, there's probably another general relativity out there
Yeah.
in all, not just in physics, in all lines of work, in all scientific pursuits. There's certain theories where you're like, okay, I just explained like a big elephant in the room here
Mm-hmm.
that everybody just kind of didn't even think about.
Right.
Like there could be, for stuff we know about in physics, there could be stuff like that for the origin of life on Earth.
Yeah. Mm-hmm.
Everyone's like, yeah, okay. Everyone's like in polite company. It's like, yeah. Like somehow it started.
Mm-hmm. Right.
Nobody knows.
I find it wild that that's so elusive.
Yeah, it's strange. In the lab,
It's
you can't
strange
replicate.
that it's so elusive.
I think it's a general relativity thing. There's going to be something. It's going to involve aliens and wormholes and dimensions that we don't quite understand, or some field that's bigger than like. It's possible, maybe not. It's possible that it's a field that is different, that will feel fundamentally different from chemistry and biology. It'll be maybe through physics. Again, maybe the key to the origin of life is in physics. And the same there, it's like a weird neighbor is consciousness. It's like, all right.
A weird neighbor, yeah.
It's like, okay, so we all know that life started on Earth somehow. Nobody knows how. We all know that we're conscious. We have a subjective experience of things. Nobody understands that.
Right.
The people have ideas and so on.
Right.
But it's such a dark sort of, we're entering a dark room where a bunch of people are whispering about like, hey, what's in this room? But nobody has a effing clue. So, and then somebody comes along with a general relativity kind of conception where like reconceives everything. And you're like,
It's like a watershed moment.
Yeah.
Yeah.
Yeah, and it's there, and until
it's there,
we're living in we're living in a time until that theory comes along, and it'll be obvious in retrospect.
Yeah.
But right now we're
right. Well, it was obvious to no one that space-time was curved, but even Newton understood something wasn't right. So he knew there was something missing, and I think that's always fascinating when we're in a situation where we're pressure testing our own ideas. He did something remarkable, Newton did, with his theory of gravity, just understanding that the same phenomenon was at work with the Earth around the sun as the apple falling from the tree. That's insane. That's a huge leap. Understanding that mass, inertial mass, what makes something hard to push around, is the same thing that feels gravity, at least in the Newtonian picture, in that simple way. Unbelievable leap. Absolutely genius. But he didn't like that the apple fell from the tree even though the Earth wasn't touching it.
Yeah, the action at a distance thing.
The action at a distance thing.
That is weird too.
Well, but
that is a really weird one.
It's really weird. But see, Einstein solves that. Relativity solves that. Because it says the Earth created the curve in space. The apple wants to fall freely along it. The problem is the tree's in the way. And the tree's the problem. The tree's actually accelerating the apple. It's keeping it away from its natural state of weightlessness in a gravitational field. And as soon as the tree lets go of it, the apple will simply fall along the curve that exists.
I would love it if somebody went back to Newton's time
and told him all this.
Probably some hippie would be like, it's a gravity is just the curvature in space time, man. I wonder if he would be able to. I don't think there's every idea has its time. He might not even be able to load that in. I mean that sometimes even the greatest geniuses, I mean, you can't.
Like you need too out of context.
You need to be standing on the shoulders of giants and on the shoulders of those giants and so on.
I heard that Newton used that as an unkind remark to his competitor Hooke.
Oh no. The people talk shit even back then.
Yeah,
I
trash
love it.
talking.
It's one of the hilarious things about humans in general, but scientists too, like these huge minds.
Mm.
There's these moments in history where you'll see this in universities, but everywhere else too.
Yeah.
Like you have gigantic minds, obviously
Mhm.
also coupled with everybody has an ego. And like sometimes it's just the same soap opera that played out amongst humans everywhere else. And so you're thinking about the biggest cosmological objects and forces and ideas, and you're still like jealous
Right.
and
I know. It's
your office is
fascinating.
bigger than my
I
office.
know.
This chair, this or maybe you got married to this person that I was always in love with, and there's a
Right.
betrayal or
Right.
something.
The one woman in the department.
Yeah, the one woman in the department. Yeah. And it's just, I mean, but that is also the fuel of innovation, that jealousy, that tension, that's human.
Mm.
That's
Well, you know the
human nature.
expression, I'm sure, the battles are so bitter in academia because the stakes are so low.
That's a beautiful
Yeah.
way to phrase it. But also, like, we shouldn't forget, I mean, that I love seeing that even in academia because it's humanity.
Mhm.
The silliness, there's a degree to academia where the reason you're able to think about some of these grand ideas is because you still allow yourself to be childlike.
Oh,
Because
yeah.
there's a childlike
Oh,
nature to
there's
be
no
ask the big
question.
questions.
Oh,
But
yeah.
children can also be like
Children.
children. So like you don't, I think when in a corporate context and maybe the world
Mhm.
forces you to behave, you're supposed to be a certain kind of way.
Mhm.
There's some aspects, and it's a really beautiful aspect to preserve and to celebrate in academia, is like you're just allowed to be childlike in your
Yeah.
curiosity and your exploration. You're just exploring, asking the biggest questions. So
Mhm. The best scientists I know often ask the simplest questions. They're really first of all, there's probably some confidence there, but also they're never going to lie to themselves that they understand something that they don't understand. So even this idea that Newton didn't understand the apple falling from the tree, had he lived another couple hundred of years, he would have invented relativity because he never would have lied to himself that he understood it. He would have kept asking this very simple question. And I think that there is this childlike beauty to that. Absolutely.
yeah, just some of the topics. I don't know why I'm stuck to those two topics of origin of life and consciousness, but there's
I'll talk about this.
some of the most brilliant people I know
Hmm.
are stuck, like, just like with Newton and Einstein. They're stuck on that. This doesn't make sense. I know a bunch of brilliant biologists, physicists, chemists that are thinking about the origin of life. They're like, this doesn't. I know how evolution works. I know how the biological systems work, how genetic information propagates, but like this part, the singularity at the beginning doesn't make sense.
Hmm.
We don't understand. We can't create it in the lab. They're bothered. Every single day, they're bothered by it, and that being bothered by that tension, by that gap in knowledge is, yeah, that's the catalyst. That's the
That's the
fuel
catalyst.
for the for the
Discovery.
for discovery.
Yeah, absolutely. The discovery is going to come because somebody couldn't sleep at night and couldn't rest.
So in that way, I think black holes are a kind of portal into some of the biggest mysteries of our universe. So it's a good terrain on which to explore these ideas. So can you speak about some of the mysteries that the
Mhm.
black holes present us with?
Yeah, I think it's important to separate the idea that there are these astrophysical states that become black holes um, from being synonymous with black holes, because black holes are kind of this larger idea, and they might have been made primordially when the Big Bang happened, and there's something flawless about black holes that makes them fundamental, unlike anything else. So they're flawless in the sense that you can completely understand a black hole by looking at just its charge, electric charge, its mass, and its spin. And every black hole with that charge, mass, and spin is identical to every other black hole. You can't be like, oh, that one's mine. I recognize it. It has this little feature, and that's how I know it's mine. They're featureless. You try to put Mount Everest on a black hole, and it will shake it off. in these gravitational waves. It will radiate away this imperfection until it settles down to be a perfect black hole again. So there's something about them that is unlike, and another reason why I don't like to call them objects in a traditional sense, unlike anything else in the universe that's macroscopic. It's kind of a little bit more like a fundamental particle. So an electron is described by a certain short list of properties: charge, mass, spin, maybe some other quantum numbers. That's what it means to be an electron. There's no electron that's a little bit different. You can't recognize your electron. They're all identical in that sense. And so in some very abstract way, black holes share something in common with microscopic fundamental particles. And so what they tell us about the fundamental laws of physics can be very profound. And it's why even theoretical physicists, mathematical physicists, not just astronomers who use telescopes, they rely on the black hole as a terrain to perform their thought experiments. And it's because there's something fundamental about them.
Yeah, general relativity means quantum mechanics, means
And it happens
singularity.
there.
And sadly, heartbreakingly so, it's out of reach for experiment at this moment, but it's within reach for theoretical.
It's in
physics.
reach for thought experiments.
For thought experiments.
Which are quite beautiful.
Well, on that topic, I have to ask you about the paradox, the information paradox of black holes. What is it?
So this is what catapulted Hawking's fame. When he was a young researcher, he was thinking about black holes and wanted to just add a little smidge of quantum mechanics, just a little smidge, wasn't going for full-blown quantum gravity, but kind of just asking, well, what if I allowed this nothing, this vacuum, this empty space around the event horizon? The star's gone, there's nothing there. What if I allowed it to possess sort of ordinary quantum properties, just a little tiny bit, nothing dramatic? Don't go crazy, And one of the properties of the vacuum that is intriguing is this idea that you can never say the vacuum's actually completely empty. We talked about Heisenberg, but the Heisenberg uncertainty principle really kicked off a lot of quantum mechanical thinking. It says that you can never exactly know a particle's position simultaneously with its motion, with its momentum. You can know one or the other pretty precisely, but not both precisely. And the uncertainty isn't a lack of ability that we'll technologically overcome. It's foundational. So that there's, in some sense, when it's in a precise location, it is fundamentally no longer in a precise motion. And that uncertainty principle means I can't precisely say a particle is exactly here, but it also means I can't say it's not. Okay. And so it led to this idea that what do I mean by a vacuum? Because I can't 100% precisely know. In fact, there's not really meaningful to say that there's zero particles here. And so what you can say, however, is you can say, well, maybe particles kind of froth around in this seething quantum sea of the vacuum. Maybe two particles come into existence and they're entangled in such a way that they cancel out each other's properties. So they have the properties of the vacuum. They don't destroy the kind of properties of the vacuum because they cancel out each other's spin, maybe each other's charge, maybe things like that. But they kind of froth around. They come, they go, they come, they go. And that's what we really think is the best that empty space can do in a quantum mechanical universe. Now, if you add an event horizon, which, as we said, is really fundamentally what a black hole is, that's the most important feature of a black hole. The event horizon, if the particles are created slightly on either side of that event horizon, now you have a real problem. Okay. Now the pair has been separated by this event horizon. Now they can both fall in, that's okay. But if one falls in and the other doesn't, it's stuck. It can't go back into the vacuum because now it has a charge or it has a spin or it has something that's no longer the property of that vacuum it came from. It needs its pair to disappear. Now it's stuck. It exists. It's like you've made it real. So in a sense, the black hole steals one of these virtual particles and forces the other to live. And if it'll escape, radiate out to infinity, and look like, to an observer far away, that the black hole has actually radiated a particle. Now, the particle did not emanate from inside. It came from the vacuum. It stole it from empty space, from the nothingness that is the black hole. Now, the reason why this is very tricky is because in the process, because of this separation on either side of the event horizon, the particle it absorbs, it has to do with the switching of space and time that we talked about, but the particle it absorbs, well, from the outside, you might say, oh, it had negative momentum, it was falling in. From the inside, you say, well, this is actually motion and time. This is energy. It has negative energy. And as it absorbs negative energy, its mass goes down. The black hole gets a little lighter. And as it continues to do this, the black hole really begins to evaporate. It does more than just radiate. It evaporates away. And it's intriguing because Hawking said, look, this is going to look thermal, meaning featureless. It's going to have no information in it. It's going to be the most informationless possibility you could possibly come up with when you're radiating particles. It's just going to look like a thermal distribution of particles, like a hot body. And the temperature is going to only tell you about the mass, which you could tell from outside the black hole anyway. Mm-hmm. You know the mass of the black hole from the outside. So it's not telling you anything about the black hole. It's got no information about the black hole. Now you have a real problem. And when he first said it, a lot of people describe that not everyone understood how really naughty he was being. He did. But some people who love quantum mechanics were really annoyed. Okay, people like Lenny Susskind, Gerard 't Hooft, Nobel Prize winner, they were mad because it suggested something was fundamentally wrong with quantum mechanics, if it was right. And the reason why it says there's something fundamentally wrong with quantum mechanics is because quantum mechanics does not allow this. It does not allow quantum information to simply evaporate away and poof out of the universe and cease to exist. It's a violation of something called unitarity, but really the idea is it's the loss of quantum information that's intolerable. Quantum mechanics was built to preserve information. It's one of the sacred principles, as sacred as conservation of energy. In this example, more sacred, because you can violate conservation of energy with Heisenberg's uncertainty principle a little tiny bit. But so sacred that it created what became coined as the black hole wars, where people were saying, look, general relativity is wrong. Something's wrong with our thinking about the event horizon, or quantum mechanics isn't what we think it is, but the two are not getting along anymore. And just to tell you how dramatic it is, so the temperature goes down with the mass of the black hole, heavier a black hole, the cooler it is. So we don't see black holes evaporate. They're way too big. But as they get smaller and smaller, they get hotter and hotter. So as the black hole nears the end of this cycle of evaporating away, it takes a very long time, much longer than the age of the universe. It will be as though the curtain, the event horizon's yanked up. Like it'll literally explode away, just boom. And the event horizon, in principle, would be yanked up. Everything's gone. All that information that went into the black hole, all that sacred quantum stuff, gone. Poof. Okay, because it's not in the radiation, because the radiation has no information. And so it was an incredibly productive debate because in it are the signs of what will make gravity and quantum mechanics play nice together, some quantum theory of gravity. Whatever these clues are, and they're hard to assemble. If you want a quantum gravity theory, it has to correctly predict the temperature of a black hole, the entropy of a black hole. It has to have all of these correct features. The black hole is the place on which we can test quantum gravity.
But it still has not been resolved.
It has not been fully resolved.
I looked up all the different ideas for the resolution. So there's the information loss, which is what you referred to.
Right.
It's perhaps the simplest, yet most radical resolution, is that information is truly lost. This would mean quantum mechanics, as we currently understand it, specifically unitarity, is incomplete or incorrect under these extreme gravitational conditions.
I'm unhappy with that. I would not be happy with information loss. I love that it's telling us that there's this crisis, because I do think it's giving us the clues. And we have to take them seriously.
For you, the gut is like
Unitarity is going to be preserved.
preserved. So quantum mechanics
We have
is
to come
holding
to the
strong.
rescue. As Lenny Susskind in his book Black Hole War says, his subtitle is My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics.
Quantum mechanics. I love it.
It's something to that effect.
So then from string theory, one of the resolutions is called Fuzzballs. I love physicists so much. Originating from string theory, this proposal suggests that black holes aren't singularities surrounded by empty space and an event horizon. Instead, they are horizonless, complex, tangled objects, aka fuzzballs, made of strings and brains roughly the size of the would-be event horizon.
Yeah.
There's no single point of infinite density and no true horizon to cross.
In some sense, it says there's no interior to the black hole. Nothing ever crosses. So I gave you this very nice story that there's no drama. Sometimes that's how it's described at the event horizon, and you fall through and there's nothing there. This other idea says, well, hold on a second. If it's really strings, as I get close to this magnifying quality and the slowing time down near the event horizon, it is as though I put a magnifying glass on things, and now the strings aren't so microscopic. They kind of smear around, and then they get caught like a tangle around the event horizon, and they just actually never fall through. I don't think that either, but it was interesting.
So it's just adding a very large number of extra complex
degrees of freedom.
Yeah.
There are no teeny tiny marbles to fall through.
But it's similar to what we already have with quantum mechanics. It's just giving a deeper,
it's
more
really
complicated...
saying the interior's just not there ever. Nothing falls in. So the information gets out because it never went in the first place.
Oh, interesting. So there is a strong statement there.
There's a strong statement there, yeah.
Okay, so soft hair challenges the classical no-hair theorem by suggesting that black holes do possess subtle quantum, quote, hair. This isn't classical hair-like charge, but very low-energy quantum excitations, soft gravitons or photons at the event horizon that can store information about what fell in.
Worth trying, but I also don't think that that's the case. So the no-hair theorems are formal proofs that the black hole is this featureless, perfect fundamental particle that we talked about, that all you can ever tell about the black hole is its electrical charge, its mass, and its spin, and that it cannot possess other features. It has no hair is one way of describing it. And that those are proven mathematical proofs in the context of general relativity. So the idea is, well, therefore I can know nothing about what goes into the black hole, so the information is lost. But if they could have hair, I could say that's my black hole, because it have features that I could distinguish, and it could encode the information that went in this way. And the event horizon isn't so serious. Isn't such a stark demarcation between events inside and outside, and where I can't know what happened inside or outside. And I don't think that's the resolution either, but it was worth a try.
Okay, the pros and cons of that one. The pros, it works within the framework of quantum field theory in curved spacetime, potentially requiring less radical modifications than fuzzballs or information loss. Recent work by Hawking, Perry, Strominger revitalized this idea. The cons is that the precise mechanism by which information is encoded and transferred to the radiation is still debated and technically challenging to work out fully, and indeed, it needs to store a vast amount of information. Okay, another one, this is a weird one, boy, is ER equals EPR.
This is probably it, though.
Oh, boy. So ER equals EPR is Einstein-Rosen bridge equals Einstein-Podolsky-Rosen bridge, posits a deep connection between quantum entanglement and space-time geometry, specifically Einstein-Rosen bridge, commonly known as wormholes. It suggests that entangled particles are connected by a non-traversable wormhole. So tiny wormholes connected. Okay.
I can say that this is not a situation where we can follow the chalk. We can't start at the beginning and calculate to the end. So it's still a conjecture. I think it's very profound, though. I kind of imagine Juan Maldacena, who's part of this, with Lenny Susskind, they were kind of like, oh, it's like ER equals EPR. They couldn't even formulate it properly. It was like an intuition that they had kind of landed on and now are trying to formalize. But to take a step back, one way of thinking about ER equals EPR, you have to talk about holography first. and holography, both Juan Maldacena really formalized it, Lenny Susskind suggested it. The idea of a black hole hologram is that all of the information in the black hole, whatever it is, whatever, entropy as a measure of information, whatever the entropy of the black hole is, which is telling you how much information is hidden in there, how much information you don't have direct access to, in some sense, is completely encoded in the area of the black hole. Meaning, as the area grows, the entropy grows. It does not grow as the volume. This actually turns out to be really, really important. If I tried to pack a lot of information into a volume, more information than I could pack, let's say, on the surface of a black hole, I would simply make a black hole. And I would find out, I can't have more information than I can fit on the surface. So Lenny coined this a hologram. People who take it very seriously say, well, again, maybe the interior of the black hole just doesn't exist. It's a holographic projection of this two-dimensional surface. In fact, maybe I should take it all the way and say, so are we. Mm-hmm. The whole universe is a holographic projection of a lower dimensional surface, right? And so people have struggled, nobody's really landed it, to find a universe version of it. Maybe there's a boundary to the universe where all the information is encoded, and this entire three-dimensional reality that's so compelling and so convincing is actually just a holographic projection. Juan Maldacena did something absolutely brilliant. It's the most highly cited paper in the history of physics. It was published in the late 90s. It has a very opaque title that would not lead you to believe it's as revelatory as it is. But he was able to show that a universe like in a box with gravity in it, it's not the same universe we observe, doesn't matter. It's just a hypothetical called an anti-de Sitter space. This universe in a box, it has gravity, it has black holes, it has everything gravity can do in it. On its boundary is a theory with no gravity. A universe that can be described with no gravity at all, so no black holes, and no information loss problem. And they're equivalent. That the interior universe in a box is a holographic projection of this quantum mechanics on the boundary. Pure quantum mechanics, purely unitary, no loss of information. None of this stuff could possibly be true. There can't be loss of information if this dictionary really works, if the interior is a hologram, a projection of the boundary. I know that's a lot.
Yeah. So there's some mathematics there, there's physics, and then there's trying to conceive of what that actually means practically for us.
Well, what it would mean for us is that information can't be lost, even if we don't know how to show it in the description in which there are black holes. It means it can't possibly be lost because it's equivalent to this description with no gravity in it at all, no event horizons, no black holes, just quantum mechanics. So it really strongly suggested that quantum mechanics was going to win in this battle, but it didn't show exactly how it was going to win. So then comes ER equals EPR, a visual way to imagine what this means. So ER has to do with little wormholes. EPR, Einstein, Podolsky, Rosen, has to do with quantum entanglement. The idea was, well, maybe the stuff that's interior to the black hole is quantum entangled, like EPR, quantum entangled, with the Hawking radiation outside the black hole that's escaping. And that quantum entanglement is what allows you to extract the information, because it's not actually physically moving from the interior to the exterior. It's just subtle quantum entanglement. And in fact, I can kind of think of the entire black hole. If I look at it, and it looks like a solid shadow cast on the sky, some region of spacetime. If I look at it very closely, I will see, oh no, it's actually sewn from these quantum wormholes, like embroidered. And so when I get up close, it's almost as though the event horizon isn't the fundamental feature on the spacetime. The fundamental feature is the quantum entanglement embroidering the event horizon.
The embroidering is just tiny wormholes. So the quantum entanglement is when two particles are connected at arbitrary distances.
And they're connected by a wormhole.
And in this case, they would be connected by a wormhole.
So the reason why that's helpful, it helps you connect the interior to the exterior without trying to pass through. the
Now,
event horizon.
the cons of this theory is highly conceptual and abstract. The exact mechanism for information retrieval via these non-traversable wormholes is not fully understood. Primarily explored in theoretical toy models. Whoa, Gemini going hard. Theoretical toy models like the anti-de Sitter space-time, rather than realistic black holes.
True. We do what we can do in baby steps.
So another idea to resolve the information paradox is firewalls. Proposed by Ameri, Maroff, Polchinski, and Sully, AMPS. This is a more drastic scenario arising from analyzing the entanglement requirements of Hawking radiation to preserve unitarity and avoid information loss. They argued that the entanglement structure requires the event horizon not to be the smooth, unremarkable place predicted by general relativity, the equivalence principle. Instead, it must be a highly energetic region, a, quote, firewall that incinerates anything attempting to cross it. Okay, so yeah, that's a nice solution. Just destroy everything that crosses this. Do you find this at all a convincing resolution to the information
I would
paradox?
say the firewall papers were fascinating and were very provocative and very important in making progress. I don't even think the authors of those papers thought firewalls were real. I think they were saying, look, we've been brushing too much under the rug. And if you look at the evaporation process, it's even worse than what you thought previously. It's so bad that I can't get away with some of these prior solutions that I thought I could get away with. There was a kind of duality idea or a complementarity idea that, oh, well, maybe one person thinks they fell in, one person thinks they never fell in, and that's okay. No big deal. They sort of exposed flaws in these kind of approaches, and it actually reinvigorated the campaign to find a solution. So it stopped it from stalling. I don't think anyone really believes that at the event horizon, you'll find a firewall. But it did lead to things like the entangled wormholes embroidering a black hole, which was born out of an attempt to address the concerns that AMPS raised. So it did lead to progress.
So for you, the resolution would...
I'm going back to the vacuum.
You go back
the empty space, the beautiful event horizon.
Yep.
I'll give up locality, meaning that I will allow things to be connected non-locally by a wormhole.
So that is the weirdest thing you're willing to allow for, which is arbitrary distance connection of particles through a wormhole. But quantum mechanics must be preserved.
I'll entertain pretty weird things, but I think that's the one that sounds promising. The implications are so dramatic because this is why you start to hear things like, wait a minute, if the event horizon only exists when it's sewn out of these quantum threads, does that mean that gravity is fundamentally quantum mechanics? Not that gravity and quantum mechanics get along and I have a quantum gravity theory and I now know how to quantize gravity. Actually, something much more dramatic. Gravity is just kind of emerging from this quantum description, that gravity isn't fundamental. And what is the only thing that we have when we go rock bottom, when we go deeper and deeper, smaller and smaller, is quantum mechanics. So all of this, like space-time looks nice and smooth and continuous, but if I look at the quantum realm, I'll see everything sewn together out of quantum threads. And that space-time is not a smooth continuum all the way down. Now, people already thought that, but they thought it kind of came in chunks of space-time. Instead, maybe it's just quantum mechanics all the way down.
Quantum threads, so these entangled particles connected by wormholes.
Yeah.
So that's how would you even visualize a black hole in that way? So it's all, it's all sort of from our perspective in terms of detecting things, the light going in, it's all still the same. But when you zoom in a lot
to the quantum mechanical scale at which you're seeing the Hawking radiation, you would be noticing that there's some entanglement between the radiation that I could not explain before and the interior of the black hole. So it's now no longer a perfectly thermal spectrum with no features that only depends on the mass. It actually has a way to have an imprint of the information interior to the black hole in the particles that escape. And so now, in principle, I could sit there for a very long time. It might take longer than the age of the universe, and collect all the Hawking radiation and see that it actually had details in it that are going to explain to me what was interior to the black hole. So the information is no longer lost.
So information is not being destroyed. So in theory, you should be able to get information.
Now, I can't do that any more than I can recover the words on that piece of paper once it's been burnt. But that's a practical limitation, not a fundamental one. It's just too hard. But when I burn a piece of paper, technically the information is all there somewhere. It's in the smoke, it's in the currents, it's in the molecules, it's in the ink molecules. But in principle, if I took the age of the universe, I could probably reconstruct, I should be able to, in principle, reconstruct the piece of paper and all the words on it.
Do you think a theory of everything that unifies general relativity and quantum mechanics is possible? So we're like skirting around it.
Yeah, we're skirting around it. I think that this is the way to find that out. It's going to be on the train of black holes that we figure out if that's possible. I think that this is suggesting that there might not be a theory of quantum gravity, that gravity will emerge at a macroscopic level out of quantum phenomena. Now, we don't know how to do that yet, but these are all hints.
Emerge. So a lot of the mathematics of anything that emerges from complex systems is very difficult to...
The transition's very difficult, right?
And so if that's the case, there might not be a simple, clean equation that connects everything.
There are examples of emergent phenomena which are very simple and clean. Like I can just take electromagnetic scattering, which is law of physics, where particles scatter just by electromagnetically. And I have a lot of them, and I have a lot of them in this room, and they come to some average. Well, I call that temperature, right? And that one number, the fact that there's one number describing all of these gazillions of particles, is an emergent quantity. There's no particle that carries around this fundamental property called temperature, right? It emerges from the collective behavior of tons and tons of particles. In some sense, temperature is not a fundamental quantity. It's not a fundamental law of nature, right? It's just what happens from the collective behavior. And that's what we'd be saying. We'd be saying, oh, this emerges from the collective behavior of lots and lots and lots of quantum interactions.
So when do you think we would have some breakthroughs on the path towards theory of everything, showing that it's possible or impossible, all that kind of stuff? If you look at the 21st century, say you're move 100 years into the future and looking back, when do you think the breakthroughs will come? So I'll give you some hard problems. And I guess my question is, how hard is this problem? What does your gut say? Because, finding the origin of life, figuring out consciousness, solving some of the major diseases. Then there's the theory of everything, understanding this, resolving the information paradox. So these puzzles that are before us as a human civilization, physics, this feels like really one of the big ones. Of course, there could be other breakthroughs in physics that don't solve this.
Yeah, we could discover dark matter, dark energy. We could discover extra spatial dimensions. We could discover that those three things are linked, that there's like a dark sector to the universe that's hiding in these extra dimensions. And that's something that I love to work on. I think is really fascinating. All of those would also be clues about this question, but they wouldn't solve this problem. I think it's impossible to predict. There has been real progress, and the progress, as we've said, comes from the childlike curiosity of saying, well, I don't actually understand this. I'm going to keep leaning on it because I don't understand it. And then suddenly you realize nobody really understood it. So I don't know. Do I think it's a harder problem than the problem of the origin of life? I think it's technically a harder problem. But I don't know. Maybe the breakthrough will come.
So when you mentioned discovering extra dimensions, what do you mean? What could that possibly mean?
Well, we know that there are three spatial dimensions. We like to talk about time as a dimension. We can argue about whether that's the right thing to do. But we don't know why there are only three. It very well could be that there are extra spatial dimensions, that there's like a little origami of these tightly rolled up dimensions. Not all of them, not all the models require that they're small, but most do. String theory requires extra dimensions to make sense, but even if you feel very hostile towards string theory, there are lots of reasons to consider the viability of extra dimensions. And we think that they can trap little quantum energies in such a way that might align with the dark energy. I mean, the numerology is not perfect. It's a little bit subtle. It's hard to stabilize them. It's possible that there are these kind of quantum excitations that look a lot like dark matter. It's kind of an interesting idea that in the Big Bang, the universe was born with lots of these dimensions. They were all kind of wrapped up in the early universe. And what we're really trying to understand is, why did 3 get so big? and why did the others stay so small?
Is it possible to have some kind of natural selection of dimensions kind of
Yeah,
situation?
there is, actually. And people have worked on that. Is there a reason why it's easier to unravel 3? Some people think about strings and brains wrapping up in the extra dimensions, causing a kind of constriction, but preferentially loosening up in 3. Sometimes we look at exactly models like that, which have to do with the origami being resistant to change in a certain way that only allows 3 to unravel and keeps the others really taut. But then there are other ideas that we're actually living on a 3-dimensional membrane that moves through these higher dimensions. And so the reason we don't notice them isn't because they're small. Maybe they're not small at all. But it's because we're stuck to this membrane. So we're unaware of these extra directions.
Is it possible that there's other intelligent alien civilizations out there that are operating on a different membrane? This is a bit of an out there question, but I ask it more kind of seriously. Like, is it possible, do you think, from a physics perspective, to exist on a slice of what the universe is capable of?
I think it is certainly mathematically possible on paper to imagine a higher dimensional universe with more than one membrane. And if things are mathematically possible, I often wonder if nature will try it out.
Yeah.
Just how people get into the strange territory of talking about a multiverse. Because if you start to say, one of the aspirations was, in the same way that we identified the law of electroweak theory of matter, that it was a single description and exactly landed on the description that matched observations, people were hoping the same thing would happen for a kind of theory that also incorporated gravity. There would be this one beautiful law, but instead they got a proliferation, all of which did okay or did equally badly. They suddenly had trouble not only finding a single one, but sort of that would just beg a new question, which is, well, why that one? And if nature can do something, won't she do anything she can try? And so maybe we really are just one example in an infinite sea of possible universes with slightly different laws of physics. So if I can do some of these things on paper, like imagine a higher dimensional space in which I'm confined to a brain and there's another brain or maybe a whole array of them, maybe nature's tried that out somewhere. Maybe that's been tried out here. And then, yes, is it possible that there's life and civilizations on those other brains? Yeah, but we can't communicate with them. They'd be like in a shadow space.
Can you seriously say we can't communicate with them?
Well,
Wait, so
no, that's fair. I'm limited in my communication
Right.
because I'm glued to the brain, but some things can move. We call the bulk, through the bulk. Gravity, for instance, a gravitational wave. So I could design a gravitational communication system,
Yeah.
and I could send gravitational waves through the bulk. And how SETI's doing with light into space, I could send signals into the bulk,
Nice.
telling them where we are and what we do and
Of course,
singing songs.
sending gravitational waves is very expensive. We don't know how to
Very
really do
expensive, very hard to localize. They tend to be long wavelength and very hard to do. A lot of energy moving
A lot of
around.
energy. So is it possible that the membranes are quote unquote hairy in other ways, like some kind of weird
It is possible that there's
quantum
other
thing?
things that live in the bulk. I mean, last night I was calculating away,
Okay,
looking at
nice.
something that lives in the bulk.
Okay, this is fascinating. So, I mean, okay, can we take a little bit more seriously about
hmm
the whole when I look out there at the stars,
hmm
I, from a basic intuition, cannot possibly imagine there's not just alien civilizations everywhere.
Yeah.
Life is so damn good. Like you said, nature tries stuff out.
Yeah. Nature's
Uh,
an experimenter.
and I just can't, just basic sort of observation, life. You said somewhere that you like extremophiles.
Oh,
Life
yeah.
just figures shit out. It
Yeah.
just finds a way to survive. Now, there could be something magical about the origin of life, the first spark, but like I can't even see that. It's just over and over and over. I bet actually once the story is fully told and figured out, life originated on Earth almost right away and did
hmm
so like billions of times in
hmm
multiple places, just over and over and over and over. That seems to be the thing that just whatever is the life force behind this whole thing seems to create life, seems to be a creator of different
Mm.
sorts.
Yeah.
The very from the very original primordial soup of things, it just creates stuff. So I just can't imagine. But we don't see the aliens, so
Right. Yeah. We don't even have to go to something as crazy as extra dimensions and brain worlds and all of that. What's happening right now in the past 30 years in astronomy, looking at real objects, is that the number of planets, exoplanets outside our solar system has absolutely proliferated. There are probably more planets in the Milky Way galaxy than there are stars. And now we have a real quandary. I don't think it's a quandary. I think it's really exciting. It becomes impossible. What you just said, I totally agree with. It becomes impossible to imagine that life was not sparked somewhere else in our Milky Way galaxy, and maybe even in our local neighborhood of the Milky Way galaxy, maybe within a few hundred light years of the of our solar system.
so my gut says like some crazy amount of solar systems have life, bacterial life somewhere at some point in their history had some bacterial type of life. Something like bacterial, maybe it's totally different kinds of life.
Mhm.
So then I'm just facing with the questions like, why have we not clearly seen
Yeah.
alien civilizations? And there, the answer, I don't find any great filter answer convincing. There's just no way I can imagine an advanced alien civilization not avoiding its own destruction. I can see a lot of them getting into trouble. I could see how we humans are really like 50-50 here.
Well, isn't that kind of appalling? I mean, just take that statement. We've only been around for a couple 100,000 years tops, you know? That is not very long. And we're at a 50-50. I mean, that's unbelievable. I mean, it's indisputable that we have created the means, at least potentially, for our own destruction. Will we learn from our mistakes? Will we avert course and save ourselves? One hopes so, right? But even the concept that it's conceivable, whales have not invented a way to kill themselves, to wipe out all whales and Earth and life on Earth.
That's one way to see it, but I actually see it as a feature, not a bug, when you look at the entirety of the universe, because it does seem that the mechanism of evolution constantly creates. You want to operate on the verge of destruction, it seems like. I mean, the predator and prey dynamic is really effective at creating, at accelerating evolution and development. It seems like us being able to destroy ourselves is a really powerful way to give us a chance to really get our shit together and to flourish, to develop, to innovate, to go out amongst the stars, or 50-50 destroy ourselves. But
Mhm.
like, which I think me as a human is a horrible thing. But if there's a lot of other alien civilizations, that's a pretty cool thing. You want to give everybody nuclear weapons. Half of them will figure it out, half of them won't. And the
You
ones
mean
that figure
everyone,
it out,
all these civilizations?
all these civilizations.
Mhm.
And then the ones that figure it out will figure out some incredible technologies about how to expand, how
Right,
to develop, and all that
right,
kind of stuff.
right. You could use a kind of evolutionary Darwinian natural selection on that, where in survival isn't just in a harsh, naturally induced climate change, but is because of a nuclear holocaust. And so, and then something will be created that is now impervious to that now knows how to survive.
Yep, exactly. So why haven't we seen them?
Right. Well, because that's a pretty big bar. So if you look at just to say, for comparison, dinosaurs, 250 million years. I mean, maybe not very bright. Didn't invent fire, didn't write sonnets.
Yeah.
They didn't contemplate the origin of the universe, but they lived.
Mm-hmm.
And in a benign situation without confronting their own demise at their own hands. Paws, hooves. So it's just a sheer numbers game. That's a long time, 250 million years. I do think, though, that life can flourish without wanting to manipulate its environment, and that we do see many examples of species on Earth that are very long-lived, very, very long-lived, and have very different states of consciousness. They have the jellyfish does not even have a localized brain. I don't think they have a heart or blood. I mean, they're really different from us. Okay. And that's what I think we have to start thinking about when we think about aliens. Those species have lived for a very, very long time. They even show some evidence of immortality. You can wound one badly, and there are certain jellyfish that will go back into a kind of pre-state and start over. So I think we're very attached to imagining creatures like us that manipulate technology. And I think we have to be way more imaginative if we're going to really take seriously life in the universe.
Yeah, they might not prioritize conquest and expansion.
Mm-hmm.
They might not be violent.
Mm-hmm. They might not be violent.
Like us humans.
They might be solitary. They might not be social. They might not move in groups. They might not want to leave records. They might, again, not have a localized brain or have a completely different kind of nervous system. I think all we can say about life is it has something to do with moving electrons around. And like neurologically, we move electrons through our nervous system. Our brain has electrical configurations. We metabolize food, and that has to do with getting energy, electrical energy in some sense, out of what we're eating. And we have organisms on the earth that can eat rocks. It's quite amazing. Minerals. I mean, talk about extremophiles. They can metabolize things that I would have thought were impossible to metabolize. And so, again, I think we have to kind of open our minds to how strange that could be, and how different from us. And we are the only example, even here on Earth, that does manipulate its environment in that extreme a way.
I mean, can you think of life as, because you said electrons, is there some degree of information processing required? So like it does something interesting, in quotes, with information.
I think there are arguments like that. How entropy is changing from the beginning of the universe to today, how life lowers entropy by organizing things, but it costs more as a whole system. So the whole entropy of the whole system goes up. But of course, I organized things today and reduced the entropy of certain things in order to get up and get here. And even having this conversation, organizing thoughts out of the cloud of information, but it comes at the cost of the entire system increasing entropy. So I do think there's probably a very interesting way to talk about life in this way. I'm sure somebody has. Mm-hmm.
Yeah. It creates local pockets of low entropy. And then the kind of mechanism, the kind of object, the kind of life form that could do that probably can take arbitrary forms. And you could think, now, if you could reduce it all to information, now you could start to think about physics. And in the realm of physics with the multiverse and all this kind of stuff, you could start to think about, okay, how do I detect those pockets of low entropy?
Mm-hmm. Yeah. I mean, people have tried to make arguments like that. Like, can I look for entropic arguments that might suggest we've done this before? The Big Bang has happened before.
So is it possible that there's some kind of physics explanation why we haven't seen the aliens? Like we said, membranes.
I don't think membranes is going to explain why we don't see them in the Milky Way. I think that is just a problem we're stuck with. Whether or not there are extra dimensions or whether or not there's life in another membrane, I think we know that even just in our galaxy, which is a very small part of the universe, 300 billion stars, something like that, a whole kind of variety of possibilities to be explored by nature in the same way that we're describing it. And I think you're absolutely right. When life was kicked off, first sparked here on Earth, it was voracious. Now, it took a really long time, though, to get to multicellularity.
Yeah.
I think that's interesting.
That's weird.
It's weird. It took a really, really long time to become multicellular. But it did not take long just to start.
Yeah. What do you think is the hardest thing on the chain of leaps that got to humans?
I would say multicellularity, which is strictly an energy problem, I think. Again, it's just like, can electrons flow the right way? And is it energetically favorable for multicellularity to exist? Because if it's energetically expensive, it's not going to succeed. And if it's energetically favorable, it's going to take off. It's really just, and that's why I also think that going from inanimate to animate is probably gray. Like the transition is gray. At what point we call something fully alive? Famously, it's hard to make a nice list of bullet points that need to be met in order to declare something alive. Is a virus alive? I mean, I don't know. Is a prion alive? They seem to do some things, but they kind of rely on stealing other DNA and replicating, and I don't know. I guess they're not alive. But I mean, the point is that it really, at the end of the day, I really think it's just, you asked if it's just physics. I mean, I think it's just these rules of energetics.
And the gray area between the non-living and the living is way simpler just on Earth. And you said it's already complicated on Earth, but it's probably even more complicated elsewhere, where the chemistry could be anything.
Carbon is really cool and really useful.
Yes,
because
nice.
it finds a lot, it's nice. It finds a lot of ways to combine with other things, and that's complexity, and complexity is the kind of thing you need for life. You can't have a very simple linear chain and expect to get life. But I don't know, maybe sulfur would do okay.
Okay, as we get progressively towards crazier and crazier ideas. So we talked about these microscopic wormholes, which, my mind is still blown away by that. But if we talk about a little bit more seriously about wormholes in general, also called the Einstein-Rosen bridges, to what degree do you think they're actually possible as a thing to study, creeping towards the possibility maybe centuries from now of engineering ways of using them, of creating wormholes and using them for transportation of human-like organisms?
I think wormholes are a perfectly valid construction to consider. They're just a curve in space-time. The topologically, which has to do with the connectedness of the space, is a little tricky because we know that Einstein's description is completely in terms of local curves and distortions, expansion, contraction, but it doesn't say anything about the global connectedness of the space, because he knew that it could be globally connected on the largest scales. This kind of origami that we're talking about, that you could travel in a straight line through the universe, leave our galaxy behind, watch the Virgo cluster drift behind us, and travel in a straight line as possible, and find ourselves coming back again to the Virgo cluster, and eventually the Milky Way, and eventually the Earth, that we could find ourselves on a connected, compact spacetime. And so topologically, there's something we know for sure, something beyond Einstein's theory that has to explain that to us. Now, wormholes are a little funky because they're topological. They create these handles and holes in these sneaky, by topological, I mean these connected spaces. And
Yeah, it's like Swiss cheese or
like
something.
Swiss cheese, and so I could have, I could have two like flat sheets that are connected by a wormhole, but then wrap around on the largest scale, all this cool stuff. There's nothing wrong with it as far as I can see. There's nothing abusive towards the laws about a wormhole, but we can reverse engineer. We were saying, oh, look, if I know how matter and energy are distributed, I can predict how space-time is curved, I can reverse engineer. I can say, I want to build a curved space-time like a wormhole. What matter and energy do I need to do that? It's a simple process, and it's the kind of thing Kip Thorne worked on, very imaginative, creative person. The problem was that he said, oh, here's the bummer. The matter and energy you need doesn't seem to be like anything we've ever seen before. It has to have like negative energy. And that's not great. There are some conjectures that we shouldn't allow things that have that kind of a property, that have negative energies. Only things that have positive energies are going to be stable and long-lived. But we actually know of quantum examples of negative energy. So it's not that crazy. There's something called the Casimir effect. You have two metal plates and you put them really close together. You can see this kind of quantum fluctuation between the plates. It's called a Casimir energy. And that can have a negative energy. It can actually cause the plates to attract or repel depending on how they're configured. And so you could kind of imagine doing something like that, like having wormholes propped up by these kinds of quantum energies. And people have thought of imaginative configurations to try to keep them propped up. Are we at the point of me saying, oh, this is an engineering problem? I'm not saying that quite yet, but it's certainly plausible.
Yeah, so you have to get a lot of this kind of weird matter.
You need a lot of this weird matter to send a person through.
Right.
That's going to be really challenging. I'm not saying it's simply an engineering problem, but it's all within the realm of plausible physics, I think.
I think that's super interesting, and I think it's obviously intricately and deeply connected to black holes.
Mm.
Is it fair to think of wormholes as just two black holes that are connected somehow?
People have looked at that. They tend to be non-traversable wormholes. They're not trying to prop them open. But yeah, I mean, some of this ER equals EPR quantum entanglement, they're trying to connect black holes. It's really cool. It's not quite following the chalk. And by that, I mean, we can't exactly start at a concrete place, calculate all the way to the end yet.
So if I may read off some of the ideas that Kip Thorne has had about how to artificially construct wormholes. So the first method involves quantum mechanics and the concept of quantum foam. And this is the thing we've been talking about. Now, to create a wormhole, these tiny wormholes would need to be enlarged and stabilized to be useful for travel. But the exact method of doing this remains entirely theoretical. No shit. You think so? So these tiny wormholes that are basically for the quantum entanglement of the particles somehow enlarged. Man, playing with the topology of the Swiss cheese would be so interesting. Even to get a hint. Mm-hmm. That would be like top 3, if not maybe even number 1 question for me to ask. If I got a chance to ask
an omniscient
being of like a question they can get an answer to, maybe with some visualization. Like the topology of the universe.
Yeah.
But I need some details.
Right.
Unfortunately, I'll get an answer that I can't possibly comprehend.
Right. It's a hyperbolic manifold that's identified across. Yeah, exactly. Yeah. You need to be able to ask a follow-up question.
Yeah, exactly. Yeah, that would be so interesting. Anyway, classical quantum strategy. The second approach combines classical physics with quantum effects. This method would require an advanced civilization to manipulate quantum gravity effects in ways we don't yet understand. There's a lot of...
In ways we don't understand.
Yeah, there's a lot of... And then there's exotic matter requirements. There's a lot of...
But I can tell you...
Stabilization.
I'm pretty sure all of them have in common the feature that they're saying, here's what I want my wormhole to look like first. So it's like saying, I want to build a building first. So they construct, there's an architecture of the space-time that they're after. And then they reverse the Einstein equations to say, what must matter and energy? What are the conditions that I impose on matter and energy to build this architecture?
Which is unfortunately a very early step of figuring out.
Right. But it's important because it's how they realized, oh, wow, they have to have these negative energies. They have to violate certain energy conditions that we often assume are true. And then you either say, oh, well, then all bets are off, they'll never exist. Or you look a little harder and you say, well, I can violate that energy condition without it being that big a deal. And again, quantum mechanics often does violate those energy conditions.
So do you think the studying of black holes and some of the topics we've been talking about will allow us to travel faster than the speed of light, or travel close to the speed of light, or do some kind of really innovative breakthroughs on the propulsion technology we use for traveling in space?
Yeah, I mean, sometimes I assign in an advanced general relativity class the assignment of inventing a warp drive.
Warp
And
drive.
it's kind of similar. So the idea is here's a place you want to get to, and can you contract the space time between you with something antithetical to dark energy, the opposite, and skip across and then push it back out again. That's all. You can do that in the context of general relativity. Now, I can't find the energy that has these properties, but I also can't find dark energy. So we've already been confronted with something that we look at the space-time. The space-time is expanding ever faster. We say, what could possibly do that? We don't know what it is, but I can tell you about its pressure. I can tell you certain features about it. And I just call it dark energy, but I actually have no idea. It's just, that name's just a proxy for what this, it should be called invisible because it's not actually dark. If it's in this room, it's not hard to see through. It's not dark. It's literally invisible. So maybe that was a misnomer. But the point being, I still don't fundamentally know what it is. That's not so terrible. That's the state of the world that we're actually in. So maybe warp drive is just kind of like a version of that. I don't know what form of matter can do that yet, but at least I can identify the features that are needed.
So figuring out what dark energy is might land some clues.
Yeah, it might. It is positive energy, and a negative pressure, which is kind of like a rubber band sort of quality. We think of pressure as pushing things outward, and dark energy has a very strange sort of quality that as things move outward, you feel more energy as opposed to less energy. The energy doesn't get lower; it gets more. And but it doesn't have the right features for the wormhole. But those are some pretty surprising features. We again can conjecture like, oh, hey, the quantum energy of the vacuum kind of behaves that way. That would be a great resolution to the dark energy problem. It's just the energy of empty space, and it's the quantum energy of empty space. That's an excellent answer. The problem is by all our methods and all the understanding we have, that energy's either really, really huge, way bigger than what we see today, or it's like zero. So that's a numbers problem. We can't naturally fine-tune the energy of empty space to give us this really weird value so that we just happen to be seeing it today. But again, we can think of a kind of dark energy that exists. So the question is just why is it such a weird value? Not how is this conceivable, because we can't conceive of it.
Yeah, but if it's a weird value, that means there is a phenomenon we don't understand.
Yes, there's absolutely a phenomenon. Nobody's going to say they're happy with that. We're all going to say there's something we don't understand, which is why we look to the extra dimensions, because then you can say, oh, maybe it has to do with the size of the extra dimensions or the way that they're wrapped up, or and so maybe it's foisted on us because of the topology, the connectedness of the higher dimensional space. These are all things that we're exploring. Nobody's landed one that's so compelling that your friends like it as much as you do.
What do you think would lead to the breakthroughs on dark matter and dark energy?
I think dark matter might be less peculiar than dark energy. My hope is that they're tied together. That would be very gratifying. These aren't just separate problems coming from different sectors, but that they're actually connected. That the reason the dark matter is where it is in terms of how much it's contributing to the universe is connected with why the dark energy is showing up right now. I would love that. That would be a solution like no other, right? And like I said, if it revealed something about dark dimensions, that would be a happy day.
Correct me if I'm wrong. So dark matter could be localized in space.
Yeah. Dark matter is localized in space. So it clumps. I mean, it doesn't clump a lot, but I mean, it's around the galaxy. It's in a halo around the galaxy.
And so people get increasingly more confident that that's a thing.
It's really compelling.
Yeah.
I mean, you see these images of galaxies clusters that pass through each other. and you can see where the light is, the luminous matter is distributed. And then by looking at the gravitational lensing, which shows you where the actual mass is distributed, so that light bends around the most massive parts in a particular way, so you can reconstruct where the mass is gravitationally, quite separate from looking at the luminous matter, which is not dark, and they are separate. Because the stuff, as they pass through each other, the interacting stuff, the luminous stuff collides and gets stuck, and you can see it colliding and lighting up. The dark stuff, which by definition it's dark because it doesn't interact, passes right through right through each other, right? And this is, I mean, it's so compelling. And there's lots of other observations, but that one is just, before you just look at it, you can see that the mass is distributed differently than the interacting luminous matter.
So dark energy is harder to get a hold of.
Dark energy is much harder to get a hold of. But, I mean, the Higgs field could have also explained dark energy.
Yeah.
If you've heard of the God particle. I don't know if you know originally Leon Letterman co-authored a book, and he wanted to call it the goddamn particle because I couldn't find it. And his publisher convinced him to call it the God particle. And he said they managed to offend two groups, those that believed in God and those that didn't.
That's a good line, too. Oh, boy.
He was very funny.
Yeah.
He was very witty.
So, Higgs turned out to be...
The Higgs, great discovery. I mean, unbelievable. There it was, build this massive collider in CERN in Switzerland, and there it is. Unbelievable. Kind of where you expect it to be. Now, the reason I say it could be dark energy is because the Higgs particle, like a particle of light, also has a field, like an electromagnetic field. So light can have this field that's distributed through all space, electromagnetic field, and you shake it around and it creates little particles. So the Higgs field is actually more important than the Higgs particle, the complement to the Higgs particle, because that's what you and I connect with to get mass in our atoms. So the idea is that our atoms are interacting with this gooey field that's everywhere. And that's what's giving us this experience of inertial mass. But we don't actually there's not a lot of quanta lying around. There's not a lot of Higgs particles lying around because they decay. So it's the field that's really important. And that field could act like a dark energy. It's just not in the right place, meaning it's not at the energy's too high to explain this tiny, tiny value today. And again, we're back to this mismatch. It's not that we can't conceive of forms of dark energy. It's that we can't make one where we're finding it.
So I wonder if you can comment on something that I've heard recently. There's some people who say, people outside of physics say that dark matter and dark energy is just something physicists made up.
Yeah.
To put a label on the fact that they don't understand a very large fraction of the universe and how it operates. Is there some truth to that? What's your response to that?
There's some truth to it, but it's really missing a huge point, which is that if we did not understand the universe as incredibly precisely as we do, it's stunning that there's modern precision cosmology. It's absolutely incredible. When COBE, which is an experiment that measured the light left over from the Big Bang in the 80s, first revealed its observations, I mean, there was applause, people were cheering, right? It was unbelievable. We had predicted and measured the light left over from the Big Bang. And because of all the precision that's happened since then, that's how we're able to confront that there's things that we don't know. And that's how we're able to confront, like, wow, this is really everything everybody has ever seen and ever will see, as far as we understand, makes up less than 5% of what's out there.
Yeah.
And so I would say, yes, we're just giving proxy names to things we don't understand. But to dismiss that as some kind of, oh, they just don't know, that it is actually quite the opposite. It is a stunning achievement to be able to stare that down and to have that so precise and so compelling that we're able to know that there's dark energy and dark matter. I don't think those are disputed anymore. And they were up until, recently. They were still disputed.
I think we're still at such early stages where we're not really even at a good explanation, right? You've mentioned a few.
Well, I can think of examples of dark matter that exists that we really know for sure are real versions of dark matter, like neutrinos. Right now, they're radiating through us. That's very well confirmed. And they're technically dark. They don't interact with light. And so we can't see them. Right now, they're raining through us. If we could see the dark matter in this room, and we absolutely know is coming from the sun, it would be wild, be a rainstorm, but they're just invisible to us. Mostly they pass through our bodies. Mostly they pass through the earth. Occasionally they get caught in some fancy detector experiment that somebody built specifically to catch solar neutrinos. So dark matter is known to exist. It's just, again, there's not enough of it. It's not the right mass to be the dark matter that makes up this missing component.
I wanted to say that I was been recently fascinated by the flat Earth people because there's been a split in the community. First of all, the community is fascinating study of human psychology, but they did this experiment where I forgot who funded it, but they sent like physicists and flat earthers to Antarctica.
Really?
And the split happened because half of them got converted into round earthers.
Wow. Well, good for them.
But then the other half just went that it was all a psyop.
Really? That's fascinating. Did somebody film that? That'd be a great documentary.
Yeah, they did. They made a whole thing. This is just at the end of last year. There was a big. I've been meaning because I think that's such a clean study of conspiracy theories because like there's so many conspiracy theories have some inkling of truth in them. Like there's some elements about the way governments operate or human psychology that it's too messy. Flat Earth to me is just clean. It's like spaghetti monster or something. Like it's just a cleanly wrong thing. So it's a nice way to
understand
discuss
the psychology.
How a large number of people can believe a thing.
Yeah, and why do they want to believe a thing? Yeah. What's very interesting is trying to use rational arguments. So that makes it even more confounding to me. I would understand more somebody who just said, look, I have faith and I believe these things and it's not about reason and it's not about logic. And okay. I mean, I don't relate to it, but okay. But to say I'm going to use reason and logic and to prove to you this completely orthogonal conclusion, that I find really interesting. So there's some kind of romance about reason and logic.
Yeah, but also there's a questioning of institutions that's really interesting and important to understand.
Well, I mean, I actually appreciate the skeptic's stance. Scientists also have to be skeptics. We have to be childlike, naive, and somewhat, in some sense, really open to anything. Right. Otherwise, you're not going to be flexible. You're not going to be at the forefront. But also to be skeptical. So I have respect for it. I guess that's exactly what I'm saying is more confusing because to invoke skepticism and then to want to use rational argument, what is the other component that's going into this? Because as you said, this is something that's easily verified. I mean, we have people in space. So you have to believe a lot more machinery. That's a lot more difficult to justify, explain as a wild conspiracy. So there's something about the conspiracy that stirs a positive emotion.
I think one of the most incredible things, I have to talk to you about this, one of the most incredible things that humans have ever accomplished is LIGO. We have to talk about gravitational waves. And the very fact that we're able to detect gravitational waves from the early universe is effing wild.
It's crazy. Yeah.
Can you explain what gravitational waves are? And we should mention you wrote a book about the humans, about the whole journey of detecting gravitational waves, and LIGO, Black Hole Blues is the book. But can you talk about gravitational waves and how the hell we're able to actually do it?
Let's just start with the idea of gravitational waves. I have to move around a lot of mass to make anything interesting happening in gravity. I mean, if you think about it, gravity is incredibly weak. I mean, right now, the whole Earth is pulling on me, and I can still get out of this chair and walk around. Like, that's insane. The whole Earth. Gravity's weak, right? So to get something going on in gravity, I need, like, big objects and things like black holes. So the idea is if black holes curve space and time around them in the way that we've been describing, things fall along the curves in space. If the black holes move around, the curves have to follow them, right? But they can't travel faster than the speed of light either. So what happens is as black holes, let's say, move around. Maybe I've got two black holes in orbit around each other. That can happen. It takes a while. A wave is created in the actual shape of space. And that wave follows the black holes as the black holes are undulating. Eventually, those two black holes will merge. And as we were talking about, it doesn't take an infinite time, even though there's time dilation, because they're both so big. They're really deforming space-time a lot. I don't have a little tiny marble falling across an event horizon. I have two event horizons. And in the simulations, you can see it bobble. And they merge together, and they make one bigger black hole, and then it radiates in the gravitational waves. It radiates away all those imperfections, and it settles down to one quiescent, perfectly silent black hole that's spinning. Beautiful stuff. And it emits E equals mc squared energy. So the mass of the final black hole will be less than the sum of the two starter black holes. And that energy is radiated away in this ringing of space-time. It's really important to emphasize that it's not light. None of this has to do literally with light that we can detect with normal things that detect light. X-rays, form of light, gamma rays are a form of light, infrared, optical, all this whole electromagnetic spectrum. None of it is emitted as light. It's completely dark. It's only emitted in the rippling of the shape of space. A lot of times it's likened closer to sound. Technically, we've kind of argued, I haven't done an anatomical calculation, but if you're near enough to two colliding black holes, they actually ring space-time in the human auditory range. The frequency is actually in the human auditory range, that the shape of space could squeeze and stretch your eardrum, even in vacuum. And you could literally hear these waves ringing. So the idea is that they're closer to something that you would want to map as a sound than it's something as a picture.
Sorry, so what do you think it would feel like to ride the gravitational wave? So like to exist. Because you mentioned eardrums.
You would literally bob around, like your orbit would change, right? If you were orbiting these black holes, two black holes, you'd be on a kind of complicated orbit.
Yeah.
But your orbit would get tossed about.
But how would the experience be? Because you're inside space-time.
Yes, I see. So the black hole is experienced within space-time as a squeezing and stretching. So you would feel it as a sort of squeezing and stretching, and you would also find your location change. Where you would fall would be redirected. So it's literally like a squeezing and stretching. Yeah. That's the way to think about it. And it's very detailed, the sort of nature of this. And but for many years, people thought, well, these gravitational waves kind of have to exist for these intuitive reasons I've described. As space-time's curved, I move the curve, the wave has to propagate through that curved space-time. But people didn't know if they really carried energy. The arguments went on and back and forth, and papers written in decades, right? But I like this sound more than an analogy, because I liken the black holes as like mallets on the drum. The drum is space-time.
Yeah.
As they move, they bang on the drum of space-time, and it rings. Remarkably, those gravitational waves, things don't interfere with them very much. So they can travel for 2 billion years, light years, in distance, 2 billion years in time, and get to us kind of as they were when they were emitted. Quieter, more diffuse. Maybe they've stretched out a little bit from the expansion of the universe, but they're pretty preserved. And so the idea of LIGO, this instrument, is to build a gigantic musical instrument. It's kind of like building an electric guitar, where the electric guitar is recording the shape of the string, and it plays it back to you through an amplifier. LIGO is trying to record the shape of the ringing drum, and they literally listen to it in the control room. Just sort of hums and wobbles. And they're like trying to play this recording drum back to you. As opposed to taking a snapshot, it's like in time.
Yeah, but to construct this guitar,
yes, this gigantic instrument.
It has to be very large and extremely precise.
It's unbelievable. I can't believe they succeeded. I can't believe they succeeded.
Yeah.
It was so insane It was such a crazy thing to even attempt. It took them 50 years. Really, that's people who started in their 30s and 40s who were in their 80s when it succeeded. I mean, imagine that tenacity, the unbelievable commitment. But the sensitivity that we're talking about is we have this musical instrument, the 4 kilometers, spanning 4 kilometers in a kind of L shape with these tunnels where there's the largest holes in the Earth's atmosphere because they pulled a vacuum in these tunnels to build this instrument. And they're measuring, they're trying to record the wobbling of spacetime, right, as it passes, this sort of undulation that amounts to less than 1/10,000th the variation in a proton over the 4 kilometers. It's an insane, insane achievement.
I love great engineering.
I don't
love
know
great
how they did it.
engineering.
I swear, I followed them around just for fun. I'm very theoretical. I don't build things. I'm always super impressed that people can translate something on the page and it looks like wires, and I don't know I'm always surprised at what it looks like. But I walked the tunnels with Ray Weiss, who won the Nobel Prize, along with Kip Thorne and Barry Barish, one of the project managers. And I walked the tunnels with Ray. It was a delight. I mean, Ray's one of the most delightful people. Kip is one of the most wonderful people I've ever known. Ray said to me, the reason why it was called Black Hole Blues is because about a month before they succeeded, he said to me, if we don't detect black holes, this whole thing's a failure. And we've led this country, down this wrong path. And he really felt like this tremendous responsibility for this project to succeed. And it weighed on him, It was just quite tremendous what the integrity, right? The scientific integrity. And the first instruments he built, he was building outside of MIT and on a tabletop. And his colleagues said, "You're not going to get tenure. You're never going to succeed." And they just kept going.
People like that, so huge teams, huge collaborations are just is how the world moves forward, because
it's an example.
It's there's a building cynicism about bureaucracies when a large number of people, especially connected to government, can be productive. Bureaucracies slow everything down. So it's nice to see an incredibly unlikely, exceptionally difficult engineering project like this succeed.
Oh, yeah.
So I understand why there's this weight on his shoulders, and I'm grateful that there's great leaders that push it forward like that.
Yeah, it really is. You see so many moments when they could have stumbled.
Yeah.
And they built a first generation machine just after 2000, and it wasn't a surprise to them, but it detected nothing. Crickets. Crickets. And they just, they have the wherewithal to keep going. Second generation. They're about to turn the machine on, quote unquote. It's a little bit of a simplification, but do their first science run. And they decide to postpone because they feel they're not ready yet. September 14th in 2015. And the experimentalists are out there. They're in the middle of the night. They're working all night long, and they're banging on the thing, literally driving trucks, slamming the brakes on to see the noise that it creates. And so they're really messing with the machine, really interfering with it just to kind of calibrate how much noise can this thing tolerate. And I guess the story is they get tired. There's an instrument in Louisiana, and there's one in Washington State, and they go home. Put their tools down. They go home. It's they leave the instrument locked, though, mercifully. And it's something like within the span of an hour of them driving back to their humble abodes that they have in these remote regions where they built these instruments, this gravitational wave washes over. I think it hits Louisiana first. It travels across the U.S., brings the instrument in Washington State. It began, over 1.5 billion years ago, before multicellular organisms had emerged on the Earth.
Yeah.
Just imagine this from like a distant view, this collision course, right? And it's the centenary. It's the year Einstein published general relativity. So it was this, 100 years. I mean, just think about where that signal was when Einstein in 1915 wrote down the general theory of relativity. It was on its way here. It was almost here.
What do you think is cooler? Einstein's general relativity or LIGO?
Well, I can't disparage my friends, but of course, relativity is just so all-encompassing.
No, but so hold on a second. All-encompassing, super powerful leap of a theory.
Yeah.
And
they built it.
They built it.
I don't know, man.
The
You
greatest
got
engineering
me.
in the
Yeah.
Because I don't know, because humans getting together and building the thing, that's really ultimately what impacts the world, right?
Yeah, I mean, I just, as I said, my admiration for Ray and Kip and the entire team is enormous. And just imagining Ray had been out there on site. He had just left to go back home. Wakes up in the middle of the night and sees it. Can you imagine? And there's a signal. There's something in the log. He's like, "What the hell is that?"
So speaking of the human story, you also wrote the book A Madman Dreams of Turing Machines. It connects two geniuses of the 20th century, Alan Turing and Godel.
Mm-hmm.
What specific threads connect these two minds?
Yeah, I was really mesmerized by these two characters. People know of Alan Turing for having ideated about the computer, being the person to really imagine that. But his work began with thinking about Gödel's work. That's where it began. And it began with this phenomenon of undecidable propositions or unprovable propositions. So there was something huge that happened in mathematics, which is people imagined that any problem in math could technically be proven to be true. Doesn't mean human beings are going to prove every fact about everything in mathematics, but it should be provable, right? I mean, it seemed it's not that wild a supposition. And everyone believed this. All the great mathematicians, Hilbert was a call of his to prove that. And Gödel, very strange character, very unusual. He was a Platonist. He literally believed that mathematical objects had a existential reality. He wasn't so sure about this reality. This reality he struggled with. He was distrustful of physical reality, but he absolutely took very seriously Platonic reality and often his own way of thinking. And he proved that there were facts, even among the numbers, that could never be proven to be true. To think about that, how wild that is, that even a fact about numbers seems very simple, could be true and unprovable, could never exist as a theorem, for instance, in mathematics, unreachable. This incompleteness result was very disturbing. Essentially, it's equivalent to saying there's no theory of everything for mathematics. Mm-hmm. It was very disturbing to people, but it was very profound. And Alan Turing got involved in this because he was thinking about uncomputable numbers. Mm-hmm. So, and that led him, what's an uncomputable number? A number like 0.175. It just goes on forever with no pattern. And I can't even figure out how to generate it. There's no rule for making that number. And he was able to prove that there were such things as these uncomputable, effectively unknowable numbers. That might not sound like a big deal, was actually really quite profound. He was relating to Gödel intellectually, right, in the space of ideas. Mm-hmm. But he goes a very different path, almost philosophically the opposite direction. He starts to think about machines. He starts to think about mechanizing thought. He starts to think, what is a proof? How does a mathematician reason? What does it mean to reason at all? What does it mean to think? And he begins to imagine inventing a machine that will execute certain orders, mechanize thought in a specific way. Well, maybe I can get a machine. I can imagine a machine that does this kind of thinking, and that he can prove that even a machine could not compute these uncomputable numbers. But where he ends up is the idea of a universal machine that computes, essentially can take different software and execute different jobs, right? We don't have a different computer to connect to the internet than we do to write papers. It's one machine and one piece of hardware, but it can do all of this huge variety of tasks. And so he really does invent the computer, essentially. And famously, he uses that thinking in a very primitive form in the war effort, where he's recruited to help break the German Enigma code, which is heavily encrypted and largely believed to be uncrackable code. And people believe that Turing and his very small group actually turned the tide of the war in favor of the Allies precisely um, by using a combination of this thinking and just sheer ingenuity and some luck. um, but the other profound revelation that Turing has is that, well, maybe we're just machines, right? And just biological machines. And this is a huge shift for him. It feels very different from Godel, who doesn't really believe in reality and thinks numbers are platonic realities, and Turing kind of thinking we're kind of like we're actually machines and we could be replicated. So of course Turing's influence is still widely felt
on many levels. So
on many levels, yeah.
In complexity theory, in theoretical computer science and
all over the
mathematics, but
place,
also in
yeah.
philosophy with his famous Turing test paper. So, like you said, conceiving like what is the connection that I guess Godel never really made between mathematics and humanity. Turing did. But I think there's another connection to those two people, is that they're both in their own way kind of tormented humans.
I think they were very tormented.
What aspects of that contributed to who they are and what ideas they developed?
I mean, I think so much. I don't want to promote the kind of trite trope of the mad genius. You know, if you're brilliant, you are insane. I don't think that. I don't think if you're insane, you're brilliant. But I do think if somebody who's very brilliant, who also chooses not to go for regular gratification in life, they don't go for money, they don't necessarily value creature comforts, they're not leveraging for fame. I mean, they're really after something different. I think that can lead to a kind of runaway instability, actually.
Yeah.
Sometimes. So they're already outside of kind of social norms. They're already outside of normal connections with people. They've already made that break. And I think that makes them more vulnerable. So Godel, did have a wife and a strong relationship, as far as I understand, and was a successful mathematician and ended up at the Institute for Advanced Study, where he walked with Einstein to the Institute every day. And they talked about, and he proved certain really unusual things in relativity. You made reference to these rotating galaxies we were talking, and actually Godel had a model of a rotating universe that you could travel backwards in time. It was mathematically correct. Showed Einstein that within relativity you could time travel. Just an unbelievably influential and brilliant man. But he was probably a paranoid schizophrenic. He did have breaks with reality. He was, I think, quite distrustful and feared the government, feared his food was being poisoned, and ultimately literally starved himself to death. And it's such an extreme outcome for such a facile mind, for such a brilliant mind.
I think it's important to sort of not to glorify or romanticize madness or suffering. But to me, you could flip that around and just be inspired by the peculiar maladies of a human mind, how they can be leveraged and channeled creatively.
Oh, yeah.
I think a lot of us, obviously probably every human has those peculiar qualities. I talk to people sometimes about just my own psychology, and I'm extremely self-critical. And I'm drawn to the beauty in people, but because I make myself vulnerable to the world, I can really be hurt by people. And that thing, okay, you can lay that out. That's this particular human, okay. And there's a bunch of people that will say, well, many of those things you don't want to do. Maybe don't be so self-critical. Maybe don't be so open to the world. Maybe have a little bit more reason about how you interact with the outside world. It's like, yeah, maybe. or maybe be that and be that fully and channel that into a productive life, we're all going to die in the time we have on this earth. Make the best of the particular weirdness that you have.
Mm-hmm.
And maybe you'll create something special in this world. And in the end, it might destroy you. And I think a lot of these stories are that. It's not that.
Oh, yeah.
It's not like saying, oh, because in order to achieve anything great, you have to suffer. No, if you're already suffering,
Mm-hmm.
if you're already weird, if you're already somehow don't quite fit in your particular environment, in your particular part of society, use that somehow. Use the tension of that, the friction of that to create something. I mean, that's what Nietzsche, who suffered a lot from even like stupid stuff like stomach issues, like
Oh, yeah.
that
Godel
can
had
be
all
everything.
kinds of, right.
Migraines is like
Psychosomatic or psychophysical, but.
and all those. That's the real. It's like that can somehow be channeled into a productive life. It should be inspiring. 'Cause a lot of us suffer in different ways.
Yeah. I'm a big believer in the tragic flaw, actually. I think the Greeks really had that right. You're describing it. What makes us great is ultimately our downfall. Maybe that's just inevitable. The choice could be not to be great. And I guess that's sort of what I mean by they had already broken from a traditional path because they decided to pursue something so elusive and that would isolate them to some extent inevitably and that could fail, right? And whose rewards were hard to predict even. And I do think that all the character traits that went into their accomplishments were the same traits that went into their demise. And I think you're right. You could say, well, Lex, maybe you should not be so empathetic. Cut yourself off a little bit, protect yourself, right? But isn't that exactly what you're bringing? One of the elements that you're bringing that makes something extraordinary in a space that lots of people try to break through.
Yeah, but we should mention that for every girl on Turing, there's millions of people who have tried and who have destroyed themselves and without
that
reason.
I would find it impossible to not pursue a discovery that I could imagine my way through, if I can really see how to get there. I cannot imagine abandoning it for some other reason, fear that it would be misused, which is a real fear, right? I mean, it's a real concern. I don't think in my work, since I'm doing extra dimensions in the early universe, or black holes, I feel pretty safe. But, I mean, who knows, right? Bohr couldn't think of a way to use quantum mechanics to kill people. I cannot imagine pulling back and saying, nope, I'm not going to finish this.
I'll give you a counterexample of an exceptionally brilliant person, Terence.
Brilliant.
Brilliant mathematician.
Brilliant.
He is better than, out of all the brilliant people I've ever met in the world, he's better than anybody else at working on a hard problem and then realizing when it's, for now, a little too hard.
Oh, that I can do.
And stepping away.
Yeah.
And he's like, okay, this is now a weekend problem. Because he has seen too much for him. Everybody's different. But Grigori Perelman or Andrew Wiles, who give themselves
that's a great story.
fully, completely for many years over to a problem.
Yes.
And for every Grigori Perelman.
And they might not have cracked it.
Yep. So you choose your life story.
I totally agree. Now, I'm not going to say sometimes I take too long to come to that conclusion, but I will proudly say, as most theoretical physicists should, that I kill most of my ideas myself.
Okay, so you're able to walk away.
I am absolutely able to say, that's just not. I mean, I'm not going to deny that sometimes I maybe take a while to come to that conclusion, longer than I should, but I will. I absolutely will. I will drop it. And that is any self-respecting physicist should be able to do that. The problem is with somebody like Andrew Wiles, you were describing, who to prove Fermat's last theorem, it took him 7 years. Was that the number? Something like that. He went up into his mother's attic or something and did not emerge for 7 years, is that maybe he did. He was on the right track. He wasn't wrong. But that's so, it could have been interminable. He still might not have gotten there in the end. And so that's the really difficult space to be in, where you're not wrong. You are onto something, but it's just asymptotically approaching that solution and you're never actually going to land it. That happens.
And he had a really, it would break me, straight up break me. He had a proof.
Yes.
He announced it and somebody found a mistake in it. That would just break me.
Yeah.
Because now everybody gets excited.
Right.
And now you realize that it's a failure, and to go back.
It was taking a year for people to check it. It's not the kind of thing you look over in an afternoon.
And then to have the will, to have the confidence and the patience to go back.
Unbelievable story.
Rigorously work through it.
It's a great story.
But then there's another great story. Grigori Perelman, who spent 7 years and turned down the Fields Medal. He did it all alone. Right. And now after he turned down the Fields Medal and the Millennium Prize, proving the Poincare conjecture, he just walked away.
Yeah. Now that's a very different psychology. That's wired differently.
Doesn't care about money, doesn't care about fame, doesn't care about anything else.
Yep.
In fact,
where is he now?
In St. Petersburg, Russia, trying to get a conversation with him. It turns out when you walk away and you're a recluse and you enjoy that, you also don't want to talk to some weird dude in a tie. So it turns out I'm trying.
Well, if you look at someone like Turing, his eccentricities were completely different, right? It's not as though there's some mold, and I really don't like it when it's portrayed that way. These are really individuals who were still lost in their own minds, but in very different ways. And Turing was openly gay, really, during this time. He was working during the war, World War II, so we understand the era, and it was illegal in Britain at the time, and he kind of refused to conceal himself. There was a time when the kind of attitude was, well, we're just going to ignore it. But he had been robbed by somebody that he had picked up somewhere. I think it was in Manchester. And it was such a small thing. I don't know what they took. It took like nothing. It was nothing. But he couldn't tolerate. He goes to the police and he tells them. And then he's arrested. He's the criminal because it involved this homosexual act. Now, here you have somebody who made a major contribution to the Allies winning the war. I mean, it's just unbelievable, not to mention the mathematical genius. I mean, he saved the lives of the people that were doing this to him. And they essentially chemically castrated him as a punishment. That was his sentence. And he became very depressed and suicidal. And the story is he was obsessed with Snow White, which was recently released. And he used to chant one of the little, I don't know if you would call them poem songs, dip the apple in the brew, let the sleeping death seep through, was a chant from Snow White. And the belief is that he dipped an apple in cyanide and bit from the poison apple. Now, I don't know if this is apocryphal, but people think that the apple on the Macintosh with the bite out of it is a reference to Turing. Now, some people deny this.
That's nice.
But some people say he did that so his mother could believe that maybe it was an accident. But quite a terrible end.
Yeah, but two of the greatest humans ever.
I think the reason why I tie them together, not just because ultimately their work is so connected, but because there's this sort of impossibility of understanding them. There's this sort of impossibility of proving something about their lives, that even if you try to write factual biography, there's something that eludes you. And I felt like that's kind of fundamental to the mathematics, the incompleteness, the undecidable, the uncomputable. So structurally, it was about what we can kind of know and what we can believe to be true but can't ever really know.
Yeah, limitations of formal systems, limitations
Exactly.
of
Biography, limitations of fiction and nonfiction.
limitations. So there's so many layers to you. So one of which there's this romantic notion of just understanding humans, exploring humans, and there's the exploring science, there's the exploring the very rigorous, detailed physics and cosmology of things. So there's the kind of artistry. So I saw that you're the chief science officer of Pioneer Works, which is mostly like an artist type of situation. It's a place in Brooklyn. Can you explain to me what that is and what role does art play in your life?
Yeah. I can start with Pioneer Works. Pioneer Works, in some sense, it was inevitable that I would land at Pioneer Works. It felt like I was marching there for many years, and just it came together again like at this collision. It was founded by this artist, Dustin Yellen, very utopian idea. He bought this building, this old iron works factory called Pioneer Iron Works in Brooklyn. It was in complete disrepair, but a beautiful old building from the late 1800s. And he wanted to make this kind of collage. Dustin's definitely a collage artist, works in glass, very big pieces, very imaginative and wild and narrative and into nature and consciousness. And I think he wanted to do that with people. He wanted a place of a collage, a living example of artists and scientists. And it was founded by Dustin, and Gabriel Florence was the founding artistic director. It was started just before Hurricane Sandy. I don't know if people feel as strongly about Hurricane Sandy as New Yorkers do, but it was a real moment around 2012, 2013. Sort of paused the project, and you can even see the kind of water line on the brick of where Sandy was. I came in and collided with these two shortly after that, and it really was like a collision. I'm science, Their art. Gabe makes everything, builds everything with his bare hands. Dustin's a dreamer. They love science. They really wanted science, but science is hard to access. I have always loved the translation of science in literature, in art. I love fiction writers, like really literary fiction writers who dabble thinking about science. And I very firmly believe science is part of culture. I know it to be true. I don't think of myself as doing outreach or education. I don't like those labels. I'm doing culture. An artist in their studio working out problems, understanding materials, building a body of work. Nobody says to them when they exhibit, why are you doing outreach or are you doing education? It's the logical extension. So I feel that if you've had the privilege of knowing some of these people, of seeing a little bit from the summit, if you've had a little glimpse yourself, that you bring it back to the world. So we, boom, exploded. Pioneer Works became science and art. It's not artists who all do science or scientists who do art. It's real hardcore scientists talking about science and a lot of live events. We have a magazine called Broadcast where we feature all of the disciplines rubbing together, artists working on all kinds of things. When I first started doing events there, my first guest, like you, I was talking to people. And this was like, I know how to talk to people because I know these guys. And I've been on the interviewee side so much. I know exactly, it was like fully formed for me how to do those conversations.
Yeah, you're extremely good at that also.
Yeah, thank you. I appreciate that. You learn how to do it too, though. I mean, I don't think the first one I did, I think I've learned, right? And you get better, which is really interesting. And I love to study. I think you do too. I really look into the material and I love science. I really do. I want to talk to a CRISPR biologist because I don't understand it and I want to understand it.
And I saw there's a bunch of cool events and very, very fascinating variety of humans.
Yes, we have a really fascinating variety of humans. That's a good way of putting it.
Yeah, so it made me put in my mental map of like, it's a cool place to go and visit when in New York.
Yes, you have to come see us. I think you would love it.
Also, I should mention fashion. I've seen you do a bunch of talks, and there's a lot of fashion.
Oh, yeah. Oh, my God.
Appreciation of fashion going on.
You're giving me an opportunity to give a shout out to Andrea Lauer, who's a designer who makes these amazing jumpsuits that I often wear in a lot of my events. She has a jumpsuit design line called Risen Division, and she just makes these incredible, they're fantastic. We also design patches for all of our events. So there are these string theory patches and consciousness patches. And
We should show this as overlays.
right.
Hopefully there'll be nice pictures floating about everywhere.
So, I think all of this is just, I just like to experiment with life. I think making the magazine was a big, wild experiment.
You said with life?
With life.
Nice.
Yeah. This kind of idea that we were just describing is, I find it hard to stop the momentum if I think I could make something. I have to try to make it. And to me, this is the closest I come to experimentation and collaboration. Because even though I collaborate theoretically, I have great collaborators, Brian Greene, Massimo Perotti, Dan Cabot. These are my really close collaborators. A lot of theoretical physics is alone, and you're in your mind a lot. This is something that really was built, this triad of Dustin, Gabe, and I, and all the amazing people who work there and our amazing board. We really are doing it together. You take one element out and it starts to change shape. And that's a very interesting experience, I think. And making things is an interesting experience.
Since you mentioned literature, is there books that had an impact on your life, whether it's literature, fiction, nonfiction?
I love fiction, which I think people expect me to read a lot of sort of sci-fi or nonfiction. I mostly read fiction. I had a syllabus of great fiction writers that had science in it. And I love that syllabus.
Can you ever make that public or no?
Yeah, I suppose I could. But I can tell you some of them as they come to mind. Katsuo Ishiguro, who won the Nobel Prize, wrote Remains of the Day, probably most famously. His book, Never Let Me Go, it's unbelievable, totally devastating, stunning. I say I really love literature. So when people can do that with these very abstract themes, it's sort of my favorite space for literature. Martin Amis wrote a book that runs backwards, Time's Arrow. I love some of his other books even more, but Time's Arrow is pretty clever.
So you like it when these non-traditional mechanisms are applied to tell a story that's fundamentally human, that there's some
and the beauty of
tragic...
the language. Like, I really appreciate that. Even Orwell is amazing. Hitchens writing on Orwell is amazing. There were some plays on the syllabus. I have to think of what else was in there, but there was one book that I think was kind of surprising that I think is an absolute masterpiece, which is The Road. And you might say, in what sense is The Road a science? Well, first of all, Cormac McCarthy absolutely loves scientists and science. And you can feel this very subtle influence. And that book is, it's a really remarkable, precise, stunning, ethereal, all of these things at once. And there's no who, what, where, when, or how. You might guess it's a nuclear event that kicks off the book. Or a lot of people know The Road, I think, from the movie, but really the book is magnificent. And it's very, very abstract, but there's a sense to me in which it is, science is structuring.
And still, fundamentally, that book is about the human story,
the
absolutely.
Human connection. The boy.
Yeah, so the science plays a role in creating the world, and within it, there's still really it's a different way to explore human dynamics in a way that's maybe lands some clarity and depth that maybe a more direct telling of the story will not. Yeah, and even surreal worlds that, I mean, to me, I don't know why, but I return to Orwell's Animal Farm a lot, and there's these kind of like. It's another art form to be able to tell a simple story with some surreal elements.
Yeah.
Well, just simple language.
Oh, Animal Farm's incredible. In fact, some of the I've kind of played with, some animals are more equal than others. There are in Godel, Turing's work, there were some infinities that are bigger than others.
Yeah, there's certain books just kind of inject themselves into our culture in a way that just reverberates and I don't know, creates culture, not just like influences. It's just like it's quite incredible how writing and literature can do that.
Yeah.
If you could have one definitive answer to one single question, this is the thing I mentioned to you.
So hard.
Yeah. Well, there's an oracle and you get to talk to that oracle. You can ask multiple questions, but it has to be on that topic. So just clarify. What mystery of the universe would you want that oracle to help you with?
It's funny. I should say the obvious thing, but I almost feel like it would be greedy. I think I have a complicated response to this. The obvious thing for me to say would be I want to understand quantum gravity, or if gravity's emergent. It's not even something I work on day to day. I mostly just look with interest at what others are doing, and if I think I can jump in, I would, but I'm not jumping into the fray. But obviously that's the big one. And there is a sort of sense that with that will come the answers to all these other things. My complicated relationship is that, part of the scientific disposition isn't having stuff you don't know the answer to. I mean, we're not going to have all the answers, I hope, because then what? Right? It's sort of dystopian.
I totally agree with you. I like the mysteries we have.
Yeah.
I kind of had this assumption that there will always be mysteries, so you want to keep solving them.
They will lead to more. In the same way that relativity led to black holes led to the information loss paradox, or the Big Bang, or what happened before, or the multiverse. It's because we learned so much, we were able to escalate to the next level of abstraction.
Yeah, by the way, we should mention that if you're talking to this oracle, and even if you ask the obvious question about quantum gravity, I almost guarantee with 100% probability that even if all your questions are answered, it's impossible to get to the end of your questions, because it says, the oracle will say, no, you can't unify.
Then you say, well, wait.
Well, yeah, and then you say emergent, and then the oracle say, well, everything you think is fundamental is not; it's emergent. It's like, okay, well, this is we need to. There's more questions.
That's right. I mean, it's been 100 years more since relativity, and we're still picking it apart.
Yeah.
No.
Yeah. And there may be new ones. You write that eventually all our history in this universe will be erased. How does that make you feel?
Yeah, it's a tough thought. But again, I think there's a way in which we can come to terms with that's kind of poetic. You build something in the sand and then you erase it.
Yeah.
So I think it's just a reminder that we have to be concerned about our immediate experience too, right? How we are to those around us, how they are to us, what we leave behind in the near term, what we leave behind in the long term. Have we contributed, and did we contribute overall net positive? Eventually, I think it's kind of hard to imagine. But yes, all of these Nobel Prizes, all of these mathematical proofs, all of these conversations, all of these ideas, all the influence we have on each other, even the AI, eventually will expire.
Well, at the very least, we can focus on drawing something beautiful in the sand.
Yeah.
Before it's washed away. Well, this was an incredible conversation. I'm truly grateful for the work you do.
And me for your work. Thanks so much for having me.
Thank you for talking today.
Yeah, lots of fun.
Thanks for listening to this conversation with Janna Levin. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Albert Einstein on the topic of relativity. When you're courting a nice girl, an hour seems like a second. When you sit on a red-hot cinder, a second seems like an hour. That's relativity. Thank you for listening, and hope to see you next time.